name is Pete Diffley, and I'm the Senior Manager for Global Partnerships with Terrestrial. I'd like to welcome you to the Automation Village breakout sessions. The breakout sessions follow on from our virtual trade show events and allow presenters and the audience to take a deeper dive into their specialist topics. You're viewing the oil and gas stream, and Ian Clark is going to be joining us now from Quintessential Computing. And Ian, are you there?
I am, sir.
Got you. Great. Thank you for having us as well here. So you're the owner and partner with Quintessential Computing as well. And in terms of your, I guess, yeah, you've been with us for the trade show as well, which was a fun event as well. So you're going to be covering it's quantum EFM improves your measurement data quality. So I'm just going to let you work away with that. But just before I move to do that, if I can just bring up a couple of little things here, I'm just going to let everyone know that if you can please ask questions during the event as well. So the whole point of this is try and make it as interactive as possible. So you should see down in the bottom of your screen, you should see a Q&A little button. So just click on that, type in any questions, and some people had asked on the previous time we did this. They said, "Oh yeah, well I can see the questions from the previous presenter." So don't worry about that. This is the oil and gas stream, so everything's going to be kind of collated, etc. So we'll have all of that. But if you do have questions for Ian, please do ask in the Q&A chat session part. And I'm going to ask at the end. It'll be about 40 minutes that Ian will have for his presentation, and at the very end, we'll have about 10 minutes that will be for Q&A, and then we give you 10 minutes to take a break yourselves in between sessions. So that's kind of call it the housekeeping part. And you'll see as well that some of you may be going between oil and gas, water and wastewater, and cybersecurity and general automation. So you can change as well. So, when you're finished listening to Ian, if you need to jump to a different stream, just make sure that you close the session you're in. And in your invite, you should have had all the links to allow you to go between oil and gas, wastewater, and cybersecurity and general automation. So that's kind of the basic format. So Ian, back to you. I'm going to ask you if you want to share your screen. I'm going to stop sharing. And if you, so welcome once again, and thank you to our viewers who are joined in out there. And feel free to share your screen. Thank you.
All right, can everybody see that Quantum EFM up on the screen?
Perfect. Yep, we got you. Thank you.
Awesome. Okay then, let's get going. So Quantum EFM is a system of record, or one source of the truth, that represents measurement and other data in an easily accessible and auditable manner. So the application typically sits sort of downstream of the SCADA system, such as VT SCADA, or a measurement data source such as AutoSol, and yet upstream of the accounting systems and other consumers of the measurement data. So today, we're going to focus on metering data specifically, even though Quantum EFM does have some other pieces to it. I've only got 40 minutes, so that's where we're going to spend our time. So the idea of validating your measurement data, some of the consequences of bad metering data are increased occurrences of facilities not balancing and settlement invoicing processes potentially being impacted by prior period adjustments. So that is adjusting a current bill to reflect an inaccuracy on a prior bill. Some of these few examples here are consequences of poor measurement data. They convert directly into hard costs for production accounting groups and can also affect a company's reputation in the marketplace. So it's really important that we have good measurement data moving downstream into the other systems of a company. So for the purposes of this session, I'm going to be using a predefined configuration. It's kind of our lab configuration that we use for demonstrations and testing. So nothing I'm doing today is going to talk to a live system. You're just going to see simulated data, but it's fairly realistic simulated data. There are three major components that Quantum EFM is made up of. So one of them you're looking at right now is the user interface. This is where you get in and actually work with your measurement data. There are services behind the scenes that handle unattended tasks like data acquisition, scheduling reports, that kind of stuff. And then at the very back end, there's the SQL Server, which is where the data repository is. So the system is very scalable, all the way from SQL Server Express all the way up to an enterprise version. You can take advantage of all of the economies of scale that come with SQL Server. Okay, so without further ado, we'll get right into it. So pull up the Quantum Efm interface and you log in. So there's two different ways to do that. You can log in with predefined user ID and password, which is something you can configure directly in the application. A lot of companies have control networks where you may not have access to Active Directory capabilities. And so this provides a local way to access things. You can also use Active Directory authentication if you're on a domain where it says, okay, I know who you are on Windows, so when we go into Quantum Efm, I will trust you, and in you go as that credential down here. So I'll come back out, and I'll log back in as this guy. Okay, you'll notice a little lockdown in the corner here. So you can set up Quantum Efm to encrypt all of its communication, both during login and during data transmission. That's a feature of SQL Server that we fully support. So the idea is if you're using this, say as an internet type portal for some data that you want to show, the communications between the server and the client will be encrypted. Okay, so what we're looking at here is our primary interface when you first come into the system. During the breakout session, or sorry, not breakout session, during my other presentation, we talked about a lot of these things across the bottom. These are considered your asset classes. So again, we're going to be concentrating on metering today, but we could also do gas analysis, tanking, and so on and so forth, but we're going to stay over here. Up top here, we have our segmentation. So this is just a way of organizing things. This is very common in oil and gas where you have districts and areas, or you might have business units and areas, that kind of thing. So this just shows how you can quickly get to areas of interest just by clicking on those, and it'll filter the list appropriately. So that's method number one. Method number two is you can filter the list you've got in front of you here just by typing. So there's a kind of a quick primary key lookup type of idea. So if I just want to see the 1001 A's, I could do that. And I can also do fancy stuff like starts with, contains, like, and so forth. So getting access to your data quickly and very rapidly is something that is important because the user interface experience needs to be easy for this stuff. The third way you can filter your data is down here in a custom filter. So the idea here is you can provide different ways of filtering on just about any attribute or field within the system. So depending on its data type, we've got a latitude here that might be a number. So we can say inclusive, exclusive, etc. So we can define custom filters here to really whittle down the list of stuff that we have to deal with. If you've only got a handful of things, the standard stuff across the top works very well. But if you're doing, say, some auditing, or you're looking for a specific thing, this feature down here is actually really powerful. Okay, so again, we've got our filtering stuff, we've got our asset classes down at the bottom, and we've got our asset list in the middle. So in this case, it's metering. So I've got various types of meters defined in the system, liquid meters, gas meters, or mass flow, that kind of stuff. Okay, and then over in the upper right-hand corner, this is where what we call our dashboard. So when you come into the system on a daily basis, this is where your to-do list essentially is. And I'll be going over what these mean in more detail later on. Okay, configuration management. So whenever you're setting up a new system, it's helpful to be able to see how you exactly set stuff up. So one of the concepts that Quantum Efm supports is called time effectivity. So time effectivity, simply put, is the ability to represent multiple configurations over time. So generally speaking, telemetry has that feature built into it, right? Where you have daily and hourly records, and they have a particular time period associated with them. But it's also important for a system of record to be able to track changes to its configuration and to be able to audit those changes so that you can defend any issues that may come up. So the main configuration interface in Quantum Efm is accessible just like that, or with an F4, and it gives you an idea of kind of how things are structured. So on the far left-hand side here, we have our classes. So it's a time-effective, object-oriented type of approach where we group business entities, such as meters, into classes called meters, right? If we click on one of these, so we see our middle tab here fill up with instances. So these are actual records of, in this case, data sources. And then on the far right-hand side, we have our properties and our relationships to other things. So these concepts are consistent throughout Quantum EFM. So every piece of configuration in the system has this structure. And what that allows us to do is maintain this stuff in a really simple and consistent manner, and really take into account the whole time effectivity and make it as simple as possible, because it can become a little unwieldy when you start thinking about your configuration over a long time period. Okay, so meter types, let's go over those. So because we're talking metering today, there are various different meter types that Quantum EFM supports out of the box, and you can see them there. So these are usually the ones you'll run into on an oil and gas project. If there are others or ones with specific capabilities, like they may have an extra field that you want to pull in from the history, or they may have some different parameters, this list is extensible to be able to include other meter types. So as an example here, we're just going to go up to our metering telemetry profiles. So here's an example of our class. So in this case, metering telemetry profile, standard EFM and limited EFM. So what this class does is it governs your metering telemetry rules, your validation rules that you're going to use to examine the incoming measurement data for any kind of problems. Okay. Data sources, we'll touch on these really quickly. So getting our data, so it's one thing to be able to define a meter and have it, how it's configured. It's also important to have a link to your data source or your data sink. So this is sending and receiving data. Mostly receiving is what we're going to do today. So from different sources, for example, this would be a VT SCADA ROC 107, and we're using the trihedral data source for that support. Okay, so if I go and look at that, and this is again the list of data sources that you saw on the initial 10-minute overview. Okay, today what we're going to be using though is what's called the loopback adapter. So this is essentially a virtual RTU within Quantum EFM that allows us to run through all of the features of Quantum EFM without having to have an actual physical device there. Okay, so let's go into our metering setup. So there's various ways to manage your configuration. Best way to illustrate this concept of time effectivity is with examples. And as I said before, fundamentally, time effective relates to the ability of a computing system to represent configuration and telemetry with respect to time. So every query the system does always includes the question when or from when to when. So there's always that time component to it. So we're going to create our first meter here. We're just going to do it from scratch so you guys can see how that works. So right click, new. So every list you see here will have a right click menu associated with it. You've got all of the standard things you would expect from a list of things that you need to deal with, including how to create new ones. So I'm going to create a new meter, and in this case, I'm going to call it 00 test, so it shows up at the top of our stuff. And I'm going to make it, just one sec here, I'm going to make it effective at inception. So what this means is the meter will be created at the beginning of time and will be effective throughout time. I could have also decided to make this meter effective at a particular time, which means if I go back in time and look at some previous configuration, I would not see my meter until the appropriate time. And the same is true for deletions. If you delete something at a particular time, it becomes non-effective going forward, but the history is still there in the past. Again, it's a critical feature of a system like this. You've got to be able to audit everything, metering data and configuration. Okay, so we're going to create our new meter effective at inception. We're going to override a few things here, and I'm just glancing over at my script here so I get this right. We're going to go to our telemetry mechanism here, and we're going to change that to standard EFM, and I'll show you what that means in a minute. And we're also going to discontinue daily history, and we're going to configure this meter to pull in hourly history. Okay. Once we've finished, we can also put in an explanation for why we're making this change. So again, you can either make this a mandatory field or an optional field. For the purposes of the demo today, I've got it set up as optional. So I'm just going to add something in here. So for demonstration purposes, and I'll hit OK. And now we have our new meter. To get to the configuration of this meter, again, it's another right click and properties. And again, you can do this for any grid, any piece of information in the system, you can get to its properties this way. And here we see our new blank meter. So what we're going to do now is change the accounting designation. So this would be a name that the meter would be known by in an accounting system to something different. So we'll go PVR meter 000. And this kind of shows that, you know, we've got one of the downstream systems that we typically feed is PVR from CGI. And so this is a common configuration that we do see. Okay. And I'll provide another reason for change there. I can go over to review, which will show me these are my outstanding configuration changes that I've got. Here's when they're effective. And I can just say test here. I can apply that. So now I've made my change. Okay. Now, one of the things to make sense of all of this time effectivity is reports that show how the configuration has changed over time. So if I right click on any item and go down to what's called property history, I will get a report that shows me the configuration since the thing was first created. In this case, it was from inception. Let's blow that up so you guys can see it. So I've created this. Here's my reason for creating it. Here's when I created it. Here's who I was when I created it. And here's what the settings were. So it shows all of the original settings for this meter, all the way down at the bottom, at inception. And then it shows, this morning at 9:14, I updated the accounting designation to PVR meter 000. And again, there's my user ID, when I made the change, and why I made the change. So that property history report is actually really, really useful to figure out sort of how things are in time and what's compared to what. So we'll go over that in a minute here. So that's the simplest way to create a new item, is just right click new. If you've got existing items like this condensate meter, for example, I can also copy and paste that and then override the pieces I want. So in this case, maybe I'll change the accounting designation. Well, I'm going to change the name first of all, because that's the default name. So we'll call it 00 test 1 or 01 test, sorry. And we're going to put in an accounting designation of PVR meter 2. And in this case, we're going to set a location. So because we're in Western Canada, we're going to change our location to something with Dominion Land Survey look and feel. So something like this. Okay. And we're going to go ahead and save that. This time I won't put a reason in. Actually, I will. Never mind. Test 2. I'm going to paste that. So now we have two meters. One is based upon another, and one is a brand new meter. So if I have a look at the property history of this guy, it will indicate that, yes, it's been defined at inception, but it was copied from 10001-A condensate. So this kind of gives me an idea of where the information came from for this new meter. I can also use that mechanism to compare configurations. So I can highlight multiple entries, go into my property history, and by default, you'll get this crosstab sort of look here, where it shows all of the items lined up by time, and then when the changes were made. So here you see the one change I made in the first meter, but the second meter, it doesn't have that change because the PVR meter 2 was actually done when I first defined it. So just to drive this point home a little bit more, if I go back into my meter here, and I change this to PVR meter 4, for example, effective at this time. Now when I do this, okay, you're going to see that here's my initial one that I did with PVR meter 000, and then here's my other one, PVR meter 4. So what this allows you to do is really compare your configuration, not only across time, but compared to instances as well. So it gives you a really good idea of how the system is changing data or how configuration has been changed by either people or software. Okay. And finally, you would never want to configure a system like this out of the box. So there is an Excel bulk import, which allows all of this configuration to be put down in Excel and loaded en masse. All right, so we're going to get into our data acquisition side of things. So, but before we do that, I'd like to talk a little bit about services. So services are kind of the worker bees behind the scenes that handle things like data acquisition, scheduled reporting, scheduled exporting of data, and so forth. So you can run multiple of these services on your system or on your network. Some examples of where we would want to do this, they'd be very similar to the way VT-SCADA is architected. So we can distribute our collection and our processing across multiple hardware instances or virtual instances if you want, similar to what VT-SCADA has by design. Services can be deployed to provide rudimentary data acquisition, redundancy for data acquisition, and are also useful when configuring OPC in a controlled network environment. So for example, providing a local service to the OPC server So we don't have to worry about DCOM permissions and firewall problems and that kind of thing. We just have to allow Quantum EFM to talk to that service, and all of a sudden we've got a local service doing what we need with that system. Okay, so the way services work is you've got your service stuff up top here, which indicates the number of services you have, in this case 1. Then you've got your modules, which is what's running in that particular service. And then down below you have your directives, i.e. what is that service currently working on. So to give it to something to work on, I'm going to upload daily data for these 12 meters from our simulator. Okay, so to do that, I just right-click it and go to Upload, Download Telemetry. That gives me some options for what kind of upload or download I want to do. In this case, I want to highlight all of this, minus hourly, because these meters are set up as daily, but I'm going to pull in everything. Okay, I'll just hit OK for that. So while that's going, if I go to my service status, you will see, I'm just going to freeze this so you can see it. You'll see all of our directives, including where they're running and what they're running on. So it's a multi-threaded sort of environment where you can run multiple of these at the same time. So again, it's more of a scalability feature where we can either run one if we've got limited hardware and software capabilities, or we can run lots of them. You'll see here it says retrying. So the demo is set up to also simulate communication failures, which we do see in the real world. So this is kind of an example of when a SCADA system has a problem, or a device isn't talking. The system does have retry capabilities built into it. Okay, so I'll let that go. It's done. When I come back here, we'll see that my dashboard is filled in with some numbers that we're going to go over at the bulk of this presentation. Concerns, conflicts, and missing, and I'll talk about those in due course. Data acquisition can be scheduled as well. So generally you wouldn't come in every morning and right-click and upload your daily history. You'd have the system do that for you and then tell you when there's any kind of problems. So this stuff can all be scheduled as well with a variety of different mechanisms. So what we're going to do now is go over to our 2 test meters that we created. We're going to go into Upload, Download Telemetry. But in this case, I'm only going to upload my hourly history, because recall that we set these guys to be hourly. Actually, I set the first one to be hourly. Maybe we'll just do that one. Okay. And now we'll see, again, it's going off getting our stuff. It's done. And now we've got way more concerns, because now we're talking 24 times the problems versus just a single daily record. Now we've got hourly records. Again, this simulator is set up to trip over just about everything. So these numbers look really high because that's what the demo is designed to do. It's also showing that we've got about 1,500 meters to find, which right now do not have any data. So that's the missing number here. Okay. Generally speaking, for what we're doing with the demo here, we don't usually have a mix of daily and hourly, but I've done that to demonstrate the flow editor, which we're going to get into next. Okay, again, multiple selections. So if I want to look at, say, this condensate meter and this condensate meter, I can use a shift click, and I can go in and look at my telemetry. Okay, so this is, again, from my simulator. It's showing 2 meters. I've got my condensate meter A and condensate meter B. In this particular case, what we're seeing here is there's a missing record on condensate B on May 4th. And we're also seeing some validation trips here where we've got, say, a frozen value, and we've got a warning limit violation here. And again, we'll get into the details of all of this as we go. So over the top, just look at the anatomy of the system here. Up top here, we have a set of controls. So upload allows you to, whatever you're looking at, you can actually go out and do demand uploads. So this is handy when you're commissioning stuff, or if you just want to pull in, what the latest history is for a given meter, you can do it on demand. Daily, hourly, monthly. So again, a measurement system needs to be able to roll up and aggregate data into monthly and daily sort of aggregations. So the idea here is if you select, say, monthly, you will get the data shown as the monthly roll-ups for these particular 2 meters for May and April, depending on what your time period is. And that can be set over here, where in this case, we're going from April 30th forward, but we can also do things like last month, last 3 months, or something relative to our current position where yesterday, today, that kind of stuff. Okay. So if we go back to daily, We'll notice here that we've got a little dot in the line in this column. That's indicating that the data we're looking at here is daily. If I go out of these 2 meters and go back to our hourly one, I pull up the telemetry editor, you'll see that if we choose daily, this time the system has calculated the rollups because it knows the source data is hourly. So here we have our daily rollups, and if we want to see our actual hourly data, we can just click on hourly, and now we've got hour by hour what we're seeing here. You'll notice that there are 2 timestamps showing on the screen. So one is called the contract timestamp, one is the actual timestamp from the RTU. Where this becomes important is when you have a leading or lagging timestamp convention. So for example, if you flag your data at top of day, usually what happens is the timestamp indicates the beginning of the period, and it goes for a day until the next timestamp. Bottom of period is the other way around, where you're going to see situations where your timestamp is going to be the next day at 9 o'clock versus the previous day. So in this case, I've got these meters set up at top of period, which is why the contract time and the timestamp are the same. Okay. You'll also notice that it says 17, 18, 19. This indicates the contract hour that is currently being played depending on what you've got for your top of day. So for example, if I scroll down to here, you'll see that hour 0 is 8 a.m. because I have 8 a.m. as my top of day. Hour 1 is 9 a.m. and so forth. If you don't want to see both of these, you can turn that off. You can go into your appearance options here and turn off the full timestamp context. In that particular case, it will show you what timestamp is appropriate for how you want to retrieve your data. So for example, production accountants would come along and do contract time here, whereas if you're troubleshooting an RTU, you might want to look at the timestamp rather than the contract time, because this is what you're relating to in your troubleshooting. Specific, detailed, and complete. So what this lets us do is if I'm in daily mode, I see my rollups. If I want to see the details behind that, I can just click on detailed. And now I get a composite view that shows my daily rollup plus all of my details that I can edit. Okay, and you'll see that little calculator beside here indicates that this is a derived value by Quantum EFM, and it's just taking all of these values and rolling them up. So these records are time and flow weighted. So as part of your meter setup, you can say, which values are to be used as part of the calculation. So it's usually metering time and volume. And then from there, we can do flow weighted averages, flow time rated averages on pressure and on temperature. Over here, I'm just gonna get out of this guy and go back to a daily so I can show you this. So all missing are available. So you may have a situation, I think we saw it on number 2 here. Sorry, not that one. We saw a situation where we had some missing data here. So in all mode, the system will show any data you have plus any data you don't have based on your top of day, your beginning or leading or lagging time period convention. It knows which data you should have and which data you shouldn't have. So here it's showing there's a missing row on May 4th at 8 a.m. If I just want to see the data I have, I can flip to available. Or if I just want to see the data I'm missing, you get the idea. Abnormalities, what this allows us to do is a quick filter to only show us records that have problems. So in this case, we've got a missing record, which is a problem, and then we've got all of our validation faults that have occurred, and we're going to address those in due course. If I want to see everything within a given time period, I deselect this, and now I have context for how that meter's been behaving over this time period. Over here, we talked about this. Up top, edit report and trend. So what this allows us to do is whatever view we're looking at here, we can, with one click, get a report of that view. And here's our metering telemetry summary. In this case, it's aggregated by day. It's just a different way of showing it. I can also go into a metering history report, which then shows it broken out by meter. And again, you can turn on quality, telemetry, and so forth down here. We'll talk about those next. So go back to our trending, I guess we'll talk about that too. So you can go in here and you can define a trend for those 2 meters for a particular set of process values. Just like that. And of course, all this stuff can be exported to Excel, PDF, Word, it can be printed, all of that good stuff. Okay, so if I go back into my telemetry editor, and I'm in my edit mode here. Down below, we can turn on or off data quality. So depending on what you're doing, you might not want to see those things. You can turn those off. We can also add alarm and event context into our telemetry editor. So what this gives us the ability to do is when we're making our edits, we need to be able to know why we're making the edits. As part of Directive 17 in Alberta or PNG 17 in Saskatchewan, it mandates that you must have this information for measurement quality data. So if I turn on my alarms, you'll get to see that, again, this is a demo, so you're going to get lots of alarms because they look good on the screen. And we're showing that we're getting a low battery power at this particular time, low volumetric flow rate, and so on and so forth. So you can bring your alarms into the picture along with your telemetry to see how the RTU is responding to generating these numbers. Similarly, you can bring events online as well. So if you've got situations where you've maybe got a timestamp problem, or you've got a flow issue that because the orifice plate changed, those kind of events would be logged in the flow computer, and you can bring them in to see exactly what's going on. And of course, if you switch back to your report, this information is all there as well in context. So for auditing purposes, pretty powerful. I'll turn those off. Okay. Let's edit some history. So what we're going to do now, let's go back up to our main screen here. So we're going to do a single edit, a multiple edit, and some bulk edits. I guess we'll show you this. So go into here. Here we've got our single meter A1 condensate. So the meter data that we're showing here is in our standard units, which in this case is metric. When you install the system, you can tell it whether you want to be US customary units or metric for your storage. From there, you can then switch to any unit system that you have defined by just going into down at the bottom here where it says standard units. I could flip this to US customary, and now I have everything in MCF, PSI, degrees Fahrenheit, and so forth. These unit profiles are extensible, so you can define your own. I'll just go into the configuration and show you that. So down at the bottom here, you can define unit presentations, which have the ability to display particular unit types in particular unit systems, but then you can also override stuff. So for example, a common one is in the US customary system, you might want your differential pressure in inches of water column as opposed to PSI. So here's an example where we have pressures usually as PSI, but in these particular cases, we want to override that and call it inches of water. Okay. So the thing you're looking at right now is very much like a spreadsheet. So if I want to make a change, I can just go in and actually make the change. So if I want to change this one to 50, now it shows I've got a pending edit there. I can make another change, 55, and then I can go ahead and save that. When you go ahead and save it, again, we're auditing systems, so you need to give a reason for that change. I can choose from any pre-canned reason here, but it's also extensible. I could add new ones or take ones away, or I can just type in a free-form one. Once I do that, I'm going to get changes that I've made. So I've got a flag over here telling me that the telemetry has been modified. I've got a reason for the edit, and I've got my new numbers here. If I go to my report view, you will see that also in the report. So there's, again, auditability here. We're showing that these are not the original numbers from the RTU. These are edits, and here's the reason for them. If you wanted to see what's in the original values, so let's go back in here. You can right-click on this, and just like we can do property history, we can do telemetry history. And what that allows us to do is look at how this value has changed over time. So again, in this particular case, here's our meter, here's our record that we're dealing with. Here was the initial value when we uploaded from the data source, and here's our changes. Again, when I made the change, who I was, why I did it. If we make further changes, so let's say we're going to zero out this entire row because I didn't think that anything was flowing that day. So I'm going to go to estimate. There's some shortcuts here. Zero allows you to do what it says, just it zeroes out the whole row in one shot. You can also do things like bring the most recent record forward. There's an example of that. Prorate accumulations, what that does is if you have a partial record, so say you have a day's worth of flow, but it's not quite a full day, it's very close though, you can use this to make it a full day, so it makes downstream systems happy that the amount of meter time is being all accounted for. but it will prorate the volume and all of the other averages that are in that record appropriately. Okay, so again, I'm just going to zero this one out. I'm going to save that, and I'll give another reason. So now what we have is a double set of edits here. So if I go to my property history, or telemetry history rather, on this one, it's going to show me where it came from before. So here's the initial uploaded value. Here's the other change I made before the test edit. And then we've got our current value, which is the test 2 edits, where I've zeroed everything out. So you can look at all of your data this way. If I want to make, say, another change down here, I'll go ahead and maybe I'll make that most recent in this case. I'll save that. Similar to your configuration, you can also highlight multiple rows, go into your telemetry history, and now you get a comparison of these 2 records for each day and how the values have changed and whether or not there's any data quality associated with them. If you turn off this pivot function down here, it'll return you to the detail view, which allows you to examine who did it, when they did it, why they did it. All right. So in some cases, you might have a validation fault, like for example, this one is saying that our static temperature is frozen. You might look at it and you go, you know what, that's okay. I'm just going to right click on that. I'm going to acknowledge that data quality. So without editing the value, I simply said, yeah, I know I'm okay with that frozen value. The value's still good. Let's go ahead and save that. So I'll give a reason for that. Maybe, you know, transmitter failure, whatever reason you want to put in there. And so now when we look at our history for that one, okay, the value is the same. We're just showing that we went from a frozen indicator to everything's fine. Okay, telemetry management. So the ability to, we can manipulate the numbers within this editor. We can also manipulate the records. So managing telemetry allows us to do things like deleting telemetry. So if you're commissioning a meter, for example, you might have some data coming in that really isn't of any use until that meter goes live. So you want to delete it, you can go ahead and do that. Again, the deletions are also recorded in the audit trail. So if you ever need to get back to them, they are there. Rebase telemetry, what this allows us to do is if we have a timestamp problem in the RTU, where we've received some data from a data source that has the wrong timestamps, even though the data is correct, it's shifted one way or the other in time. We can also change our timestamps using the rebase telemetry function. And that, of course, is all audited, so you can always track it back to where the data came from. Revert telemetry allows you to go back to what the data source originally had. So I'll just demonstrate that one up here. So I go to my zeroed out test 2. I can say I want to revert that. Again, I can give a reason and hit OK. Sure you want to do this? Yes. And so now I've got my original data reverted back to original with the reason I gave. If I look at the telemetry history for that, and I go to this complete view, you're going to see a total history of how this thing was edited. So it came up from, it was uploaded from a system, it was changed. There's our 50 and 55. We then zeroed it out, but then we changed our mind and we brought it back from the original values. So again, pretty powerful way of looking at your data and being able to audit it and defend it if you need to. Okay, reporting, trending, and data export. So again, we kind of touched on this. The reporting is available directly from here by just clicking here and going report. So whatever you're looking at, whatever meters you're looking at would show up in a report. You could also go back to your main screen here, say highlight these two, right click, and then I can go directly to a telemetry report from here. Okay. And again, these reports can be scheduled. They can be sent to places using FTP, file system copies, printing, emailing, all of that good stuff. So a good example is, you know, I want my daily production report for the last week every day sent to me by email. System can be set up to do that. Trending, we talked about that. Exporting telemetry. So if we go back into our telemetry editor here, this data here, we might want to play around with it, say in Excel, or we might want to, you know, run it into some other program. Excel is usually the one that happens here. Anyway, I can right click on that and go export. And it allows me to either select everything I've got or just my selected items, and I can send it to the clipboard, Excel, or a CSV file or a printer. So with one click here, I now have an Excel representation of that flow data, which I can slice and dice to my heart's content. So if you've got specific operations that Quantum EFM doesn't know about that you need to perform on the data, getting the data out of the system is not hard. All right, let's talk about our data validation. So our data validation rules themselves are set up in what we call telemetry profiles. So a telemetry profile is a set of rules that can be associated with one or more meters. So in this case, I've got two of them set up in the system. One is called standard EFM and one's called limited EFM. The difference between the two is a limited EFM has less history retention storage in the device. So the idea there is I wanted to create some profiles that would show all of the features of data validation, and the limited EFM is going to help us with that, especially when we talk about conflicts. So if I scroll down here, you'll see that, data processing here, missing data tolerance. So how long are we willing to wait for data before we declare it missing? Retention period, within what time period are we expecting data from the data source, and so forth. Down at the bottom here, for each process value, we can also set up a set of validation rules. So for static pressure, maybe we don't want it to validate that number if we're not flowing. So we can automatically suppress that. We've got our high and warning limits, which roughly refer to your instrument limits, which would be your alert, and your calibration limits, which would be your warning. Consecutive frozen value periods. So if you're daily, this would represent a day, hourly is hourly. You can say that these three fields here allow you to define what is considered a frozen value. So in this case, I'm saying I want to see an absolute difference of 0.1, in this case, kPa, and I want to see it every single time. But I could set this up to say, I want to see percent difference or relative percent difference. So you can do different things to define what a frozen value means in your system. And again, for meters, if I go ahead and look at, say, these three, you'll see that a telemetry profile is associated with each meter. So this can be one-to-one. You can have one telemetry profile for every single meter if you want it that way, or you can have a set of them, or you can have one that's global for your entire set of meters. It's up to you. Okay, so with that in mind, let's talk about concerns, conflicts, and missing. I'm going to start with missing and work our way back. So what missing does is allows you to see at a glance what you're missing, essentially, right? So we've got a situation here where we've never talked to any of these devices yet. We have a tolerance of 48 hours, but we're not seeing any data for these particular meters. So what we can do is initiate our upload from there. So if we see a meter that we want data for, so for example, this C3, or condensate C rather, I can upload that directly from here. And as I do that, we should see condensate meter 3 drop off the list as it goes. And again, we see back on our switchboard, a number of missing data meters has decreased by 1. So I'm going to show you another thing we can do here. So if I go into, say, this test meter that I've got, and I want to delete everything in May, because for whatever reason, I want to get this data back. So I'm going to go in here and do our managed telemetry. And in this case, I'm going to delete it. And I'm going to say, maybe it was a calibration problem or something like that. Sure you want to do this? Yes. Okay, so now we're showing these as missing records because we have deleted them. Again, with telemetry history, you can still go back and see what they were by doing the show deleted thing. So the idea is that anytime we delete something, it's more for convenience, but the system still keeps track of it in order for it to maintain its audit trail. So now if I go back to my missing data, I see my 101 condensate meter here, and it's showing that the latest data it thinks it has is April 30th, which is true because I deleted everything in May. Here's our current time, here's our tolerance, here's how far we're out. So this will give you an idea at a glance of what you're missing. Missing data also falls into this other sort of scenario where you might be up to date. In this case, we are, but on May 4th, we had a gap. right? And it was only a 1 day gap. Because we have a 48-hour tolerance, this would have never shown up on the missing data because it wasn't missing for 48 hours. And then the data came back, but we're still missing a block here. So the system has the ways of detecting that kind of stuff too. Again, you can highlight your multiple meters, and you can go into Manage Missing Telemetry, which essentially gives you a predefined jump into the telemetry editor where you're looking at your missing data only. So this is the kind of a function you can do at month end where you want to see whether or not you've got any missing records that you should fill in before you send it off to production accounting. Okay. Conflicts. So what a conflict represents is a problem with the record itself, not necessarily the contents of the record. So in this case, I mentioned the limited EFM function that we had. That would provide us with the ability to have these records come in before the time period that the RTU had retention for. So in this case, the system has identified those as suspect records. Again, these can be accepted if we want to. So I go to this H2O meter here. I just go into my telemetry editor, and I go to all. Maybe in this case, I want to go for all time, so I can see everything. So for this meter, we've got data up until April 9th. Okay? But in this case, what I want to do is go to my conflicts, and I'm going to accept this data that fell before that. I can accept that, put it in there, and now you'll see that I've got my data prior to that date, and it's been accepted into the actual telemetry editor. So where this is handy is you might have another conflict. For example, you might have existing data and you receive new data for the same meter. So a conflict would be shown by the system if it was configured that way, at which point you can make a decision whether you wanted to keep the data you had or use the data that just came in. So that's essentially what conflicts represents. Concerns, this is really the meat and potatoes of stuff. So with concerns, this gives us a quick view of where our problems are and what they are. So in this case, we've got a frozen value and static temperature. We've got 6 of those. If I double click that, it'll take me right to the editor showing those problems. Again, if I only want to see those problems, I can do my abnormalities check. You can also multi-select stuff and work with your data as you see fit. Okay. So reporting and exporting. So we're just kind of finishing up here. If I go to my telemetry export, I can send this data on its way to a downstream system. Again, this could be scheduled and automatically sent to that downstream system, but essentially you're just running a period, in this case, April 1st to 30th. And we'll let that do its export. And here are the types of data that we have. So production water, in this case, we've got disposal. We've got different profiles, just like we have different validation rules. You might have a different type of file system representation that your downstream system can adopt to. So again, that's all done in our telemetry export profile, which is right here. You can associate these with 1 or more meters as well. So in a nutshell, a really quick nutshell, that is the metering component of Quantum EFM. So we've gone everywhere from data acquisition, data definition, auditing. We've got our editing features, our ability to be told by the system what is wrong and to be able to look at that in a really efficient way. And then from there, we have multiple ways of exporting that data or reporting that data as you see fit. All right, Peter, I think I'm done.
That was really, really good, Ian. Great job. That was actually, as you were going along, I was writing down, I must ask Ian this, I must ask Ian that, and you've actually answered, I think, everything.
Oh, excellent.
We have a couple of minutes just for questions as well, if anyone else would like to ask. We literally only have maybe 2 minutes, but if you haven't already, just bring this up again. So if you're kind of wondering how to do that, just make sure that you type into the Q&A box, and I'll ask Ian as well. One thing that I was kind of wondering, I mean, with the power of Quantum EFM, I mean, is it, you know, at the start, I kind of thought that this was more, just looking after configurations and I thought, yeah, very powerful, and there was some record keeping with that, and 3/4 of the way through, I realized, no, this is actually a lot more. It's really more like an asset management system, I think, is it?
Very, very much so. It's based on a core that is also used in other industries. So Quantum EFM is for oil and gas and for water and wastewater. But we also have we also have a LIMS product, our Lab Information Management System,
Yeah.
which is built on the same concept. And again, the same things go around and around, right? We've got data acquisition we've got to do, we've got validation we have to do, and we have auditing we have to do. In the lab space, all of those things they're non-optional. Like, you have to have them. So it really gets its pedigree from that sort of approach to data management.
It's really powerful. I mean, like, the audit nature to it. I mean, like I said, I wrote down, okay, so how could you do blah, blah. And anyway, so yeah, you definitely answered it. I have a question came in as well from one of our attendees, and it's how many meters can upload? In your example, you did 12.
I could upload all of them if I wanted to. So it's just really a function of your system's capacity. So in this case, I'm running it on a virtual machine on my laptop. I've got about 1,600 meters loaded. We've tested up to 3,000 on a single instance, but really it's just a function of how your hardware is able to handle those sets of meters. There is no predefined limit within Quantum EFM itself. And the fact we're using SQL Server as a backend makes it scale up really nice when you're dealing with lots and lots of data.
Fantastic. Great question that came in. Guys, we're actually just gone a little over. Maybe if someone had a quick question, I'll just hold and pause for a second. But while I'm saying that, thank you so much, Ian. That was really, really informative. And where can people find out more information?
So on our website, quintessentialcomputing.com, there's information there, or you can email sales@quintessentialcomputing.com if you have any questions, and we'll be sure to get back to you with the answers.
Fantastic. Well, that's wonderful. So Ian, thank you so much. And
you,
to our, I want to say as well, we'll definitely welcome you back again, I'm sure for another event. So that was really good. So thanks again.
Excellent. Thank you, everybody.
Super. So to our viewers tuned in right now, so if you need to change stream, I'd mentioned you need to close this meeting and go in, then go back to your invite, and you can select the stream that you need to go to. And if you then want to go after that, you can change whichever way you want. That's the way we've left this, kind of to keep it quite flexible. So what's up next? Well, we have Mervyn Betts in the oil and gas stream. So Mervyn will be joining us shortly as well, and he'll be looking at what is changing in SCADA and basically how it's going to affect us. So if you want to take, we've got an 8-minute break, but we'll be starting at the top of the hour. So if you want to go and grab a cup of coffee, cup of tea, whatever you want to have. So Ian, thanks again, and thanks to our viewers, and I'll be back shortly as well. Thank you.
Thank you.
Hi, everyone. Yeah, well, we're ready for our next hour. I'm delighted to welcome back someone who's been with us a number of times with different trade shows we've done. So Mervyn Betts, you're muted there, Mervyn. That may have been me. So let me just make sure you're there. We go.
Hey, very good.
We got you. Excellent. So Mervyn, welcome back again. Always good to have you.
Thank you.
And I guess just for those watching that may have not come across you before, so you're our long-term distributor in Calgary, in Canada, and you've been, I guess, championing all kinds of wonderful technologies over time. You're an extensive user of VT SCADA, but you've actually in past trade shows, we've actually shown things like where you've done things like drone technology and how it interfaces with different systems in very clever ways. So I said it to you, I think last time when I introduced you, that you're kind of seen as being a kind of a bit of a out of the box thinker in so many ways. So I think you wear that label very well.
Thank you. Thank you.
Excellent. So Mervyn, so you have today you're going to be discussing basically what is changing in SCADA and how that is likely going to affect us. So over to you, really. I'm going to just give you control. So if you want to share your screen, and if you can just remind people as well that so if you want to ask a question throughout, this is like one big Q&A. So even if you saw the previous questions or anything showing up in the Q&A button that I'm showing where you click, just type in your question at any time during the presentation, and I'll ask Mervyn later on. So we'll have around 40 minutes or thereabouts for the presentation, but 10 minutes then for a Q&A, and then we'll give you another break, okay, after that. So so very good. So let me just give you control. All right, you should be able to share now.
There we go. Okay. Thank you, everyone, for joining us today. I'm Mervyn Betts, as Peter introduced me, and today we're going to talk about what's changing in SCADA and how it will affect us all. And I've abbreviated a couple things out of here that I have done a much longer presentation on this, which is a couple hours, so I've kind of condensed this down. So if there are things you want more information on at the end of it, by all means, let me know. So we have two offices, one based here in Calgary and one based in Estevan. Currently, the BettsM product line is very much a SCADA system. If you actually look at sort of VT SCADA at the top with Quantum EFM, which you just heard Ian speak on, ERS automation tools, those are kind of the top end things that we have. And then down below, we have radios, Zeta Wave radios. We're going to talk a bit about those, and as well, PLC RTU devices, which is our Overo T-Box line, and then Newgate multi-variable transmitters and SignalFire. And we're going to talk a bit about the Ranger as well. So just going to start off with a quick little video here. And what's really impressive about this video for me is this is things we can do today. And this is a guy in a hoverboard. It's hydroxide powered. This is actually real. He's actually flowing the English Channel with it. This is a completely automated mine truck for Rio Tinto. And for those people that do sort of valve control and basic process control, you understand the complexity of having something this big. This is a radio system that we were involved with, and they are doing, actually put their cameras or radios right onto motorcycles and had nanosecond latency. So you actually get to ride right along with the motorcycle driver in real time, which is something, usually we have latency and these things are delayed, but you could actually be sitting in the stands and watching as the guy's going around the track and sitting with him. This here is a basketball shooting robot. Years ago, I saw something very similar to this in Hanover Mess. They can get a robot to shoot 3-point shots 100% of the time, which is a pretty amazing concept. So that to me is some pretty neat technology things. This is Atlas. You've probably seen these videos before, but if you haven't, this is an actual real robot. It is an astounding piece of equipment. As we move into the next part of the video, it's really impressive how it can react to unforeseen things. And the unforeseen things here is this man that comes up with the hockey stick, which I thought was a good Canadian reference, and does things to this robot that kind of gives it some sort of semblance of what might be happening to things in the real world. And it's a pretty impressive bit of automation when you consider all of the computers and all the protocols and all the interaction that has to go on so that this robot can actually do its job. So it's a pretty fantastic thing. And then Atlas finally succeeds in getting his box. And this video is really impressive for me because this is actually a small drone video, and we have a bit of a fixation on drones. And he's actually using a drone to actually capture a ball that he's throwing. And it's calculating all that, and then it throws it back to him. So this is a TED Talk. So at the end of this PowerPoint, you can see all the references for all these videos. But this is certainly an amazing video to see, and to see what can happen in real-time process control, what's actually happening here. So astounding. It's a really good demonstration of what AI really is. And it's just, to me, something that I think we're going to start to see this type of technology moving into our process control industries. So the agenda for today. IP telecom everywhere. We're going to talk a little bit about device and power and self-sustaining, a little bit self-aware. Hardware and software will get divorced. RTUs will have universal I/O. Custom panels will rarely be required. Data will have context. Data transforms cost money. Alarm management a little bit, and then edge device distribution. So future concept number one. We'll have a network that can support data with context to almost every square meter on the planet in 3 to 5 years. So that's been a big part of our SCADA business, is having to deal with remote things that are very, very, very difficult to get at. And I mean, some of you who are in my vintage would remember back when we had the 1200 baud and the 900 baud and 300 baud systems that we had to get data effectively over. I mean, now we're talking about megabit and gigabit connections. But really, how do things change? How will we change our behavior if bandwidth is infinite, latency is 0, and it's reliable? So I like this cartoon. It says, welcome to hell. He said, signals going down. Getting data won't be a problem. 5G, put gigabyte data at every square meter on the planet. That's an amazing concept. So we're about 3 years out, but there's some stuff I'm going to cover later on that actually we're very close to today. The other thing is the IP, the Internet Protocol, changed everything. It allowed us to do all of our phones are IP, everything is IP, all of our process control, everything we do is IP. And one of the interesting things I find is we have not taken, and beyond IP, we have not taken and leveraged that next layer to merge the voice and video and data all together into a common stream or a common database for storage. So some terminologies. Bandwidth. So bandwidth is basically the volume of data per time. Latency, it's the time interval, so how much delay we have. Latency is really important from the perspective of when we used to work with geostationary satellites, we'd have like 3/4 of a second latency. So in order for me to have a conversation with you, it'd be like the old push-to-talk radio systems. I would say hi, and then I'd wait for 3/4 of a second, and then a response would come back. And it was very difficult for people to have bidirectional voice or bidirectional anything. Data was okay, but when we were doing pull responses like Modbus protocol, latency was a really big issue. So that was always a concern for people, is how do they deal with the latency that happens in a SCADA system? Availability is the amount of time it's actually up. And again, when we look at satellite comms, we really only have 2 times per year where the availability is a massive concern. And that is 15 minutes per year at the sun transit during the spring and fall equinox. The rest of the time, the satellite system's up 100% of the time. I mean, barring maybe some tornadoes or hurricanes or things like that coming in, satellite's pretty much 100% uptime. And the only reason that affects them is just due to the thickness of the atmosphere. So if you crank your communication strength up, then you actually get through that stuff. And then reliability. Don't lose data. And this is the number one thing we've been really focused on, because in SCADA industry, we really haven't had bandwidth. We've had not too bad latency, and availability is still always a concern. So seamless handoffs using lowest cost technologies that exactly meets my needs. That's what I want. I want to just be able to move from one place to another and have everything just connect up, and I don't have to worry about that. So Wi-Fi, cellular, they all work seamlessly, but without needing to change configuration. So those are pretty impressive, but we don't have cellular everywhere yet, but it's coming. Don't want to have to carry multiple telecom plans, but we have unified SIM cards coming where we can have multi-carriers on one SIM card. We're heading for infinite bandwidth and nearly zero latency. Want to be mobile, high availability. Symmetrical is a big one. Same speed in as out. Low power and secure. So that's kind of what our ideal scenario looks like. So let's talk a little bit about 5G. We're going to start at the physical layer, the infrastructure. So 5G, if you look at currently right now, we are running around peak on 4G is about a gigabit per second, but most people see around 20 megabit per second. We're talking about heading for a minimum of 5 gigabits per second on a terrestrial link, up to 20 gigabits per second. So that's a lot of bandwidth. Now, everybody says we're never going to consume it all, but we also know that from 300 baud to 20 megabit per second, somehow we seem to have figured out how to consume it all. So the technology spec for terrestrial 5G, the big ones are bolded there. And their user experience target is 100 megabits per second downlink and 50 megabits per second uplink. And then a 1 millisecond latency. So we're going to come back to this in a minute when we talk about satellite communications. So this is the SpaceX Falcon 9 launch. This has totally changed things. And it's not the fact even that we've just had a real maverick, Elon Musk, who's driven this. But the vision was, how do we get the payloads down so we can put more devices into the sky? And that's really what's driving SpaceX and a whole bunch of other competitors in that industry. So I'm not going to go through all of this, but if you guys want to catch that video is really impressive. It actually shows you the separation and then shows you the synchronization of the rockets relanding. We'll see if we can show the synchronization here. So, satellite, what is it? Well, simply, they're a repeater. That's pretty much all it is. It's a repeater like we have in any existing radio systems. Transponders have beamwidth, very similar to what we have for cell. They have beams that they sort of, as we hand off from place to place with our cell phones, satellites are just really cell towers, but up in the sky. So usually line of sight. They don't work very well going through buildings. We find a lot of attenuation for the high frequency signals. And they're usually more power hungry than terrestrial based communications. You usually use it for higher bandwidth, television, those types of things, and a lot of unidirectional stuff for the geostationary. Latency becomes an issue in bidirectional for the geostationary, not for the LEO, and bidirectional bandwidth is relatively expensive. So this shows you all the geostationary satellites that are around the world. And there are approximately 2,000 geostationary and LEO satellites up in the sky as of about 2 years ago. We are heading for approximately 20 to 40,000 satellites up in the sky in the next 3 to 5 years. So a LEO is a low Earth orbital, and they actually rotate around the Earth or orbit around the Earth, whereas the MEO and the GEO actually rotate with the Earth. Well, the MEO doesn't, but the LEO does. This is some ideas of what's currently available on the LEO. Iridium, you're probably familiar with, but Iridium's come out with the new Edge, which is a little itty bitty plastic device that you can just drop into a panel. It's very low bandwidth still, 210 kilobits per second. And there seems to be always questions about how, what the speed availability is on that network. The geostationary you'd be familiar with, but HughesNet's come out with 3 megabit per second, meant for just being able to hang off the back of your trailer. And then we also have very low bandwidth Beacon for doing like pipeline data and things like that. So this is the big technology breakthrough. Satellites the size of about a Rubik's Cube. And they've managed to pack all of this stuff into a very, very, very compact ultralight payload, which means it's very, very less expensive to put them up into space. So what's this going to promise us? So 5G, we still are going to have the same types of speeds for satellite. Actually, that should say 5G satellite, not terrestrial on top of it. But the 1 millisecond latency, we're not going to have that anymore. That's going to be a 50 millisecond latency, which is still very, very fast for a lot of the communications we do. And we're not going to have 1 million devices per kilometer. But other than that, this spec's going to hold up, which is very, very impressive. So this is just an idea of how the LEO satellites move. And you'll see that the satellites actually orbit and have all these beams spread out over top of the Earth, and which means we can get complete coverage of the planet. So for me, that's a very, very, very telling picture as to how we are going to get 5G coverage to every square meter on the planet. So SpaceX, they're the ones that are leading right now. Pretty interesting. So they've launched 60 more Starlink satellites here earlier in the week, a couple weeks ago actually. They brought the total count's 420. SpaceX intends to open the Starlink service in North America first this year. So they're going to open it to beta for average users. They've launched about 60 satellites per month since May, and they're going to put about 400 satellites and 800 to cover North America. So that's going to be 2021. And they're going to have 1 million base stations they have approval for. So these phones, where the Iridium actually talks directly to the phone or directly to the base unit, which you buy, these are actually base stations that look more like a pizza size. And then the pizza, that base station will be a repeater to your cell phone locally. So it's going to be a very interesting deployment that comes out with SpaceX. We're still going to have fixed units on the top of vehicles or on the side of a compressor station or those types of things in order to get the data provided by the satellite system. But it will be completely available, and it's going to be about $80 a month, US, I think. So we've got the physical infrastructure for telecommunications. Let's talk a little bit about power. Device power will be self-sustaining and self-aware. So devices will become lower and lower power, batteries will get better, and power sources get stronger. So on the left-hand side, there's a power strap, which basically just from heat that, similar to what a TEG does, just generates electricity. And on the right-hand side, we have a Zeta Pack battery. And the Zeta Pack actually is fully self-aware. It's a smart battery. It's linearized, so you can actually see when it's being drawn down, where most batteries, you don't know they're empty until after it is. And it speaks Modbus, and we'll probably be speaking some other protocols in the future. So a pretty interesting concept to have a battery that has all the diagnostics and the solar regulator and things like that. And the reason I show this is because that is where systems are going, is to be sort of somewhat containerized and compartmentalized with all of their intelligence built into them. So future concept number 3, hardware and software will get divorced. So the great divorce. So using Docker or virtual machines, we'll be able to download applications to our RTUs and aggregate like a Lego kit. So what that means is we're going to have hardware and we're going to have software. And similar to apps on your cell phone, we will be able to just drop applications right onto the hardware that we need. Now, in the oil and gas industry, Class 1 Div 2 is a barrier to entry. For most applications, if you don't have a Class 1 Div 2 for a field solution, you can't enter. So now we can take all of those applications that work in all sorts of different environments, because lots of people measure flow and lots of people measure level and do all those types of things across different industries, but they don't have a requirement for Class 1 Div 2. So the application will allow us to marry the application with the required piece of hardware. So if you're not in a hazardous area, you can measure it with a very, very cost-effective piece of equipment. Or if you are in a hazardous area, then you can take care of it with a different piece of hardware that might be, instead of a couple $100, might be $1,000 or $1,500. But the concept is you only have to have one piece of software, and you only have to learn and develop on one piece of software. So currently it's too expensive to buy industrial Class 1 Div 2. Flow computers, Raspberry Pis are cheap. The flow computer software is tested and proven. Why is it not portable? So we go through a number of flow computers where everybody and their dog has a different flow computer. They have different calculations that are supposed to behave the same way as the API calculations. And everybody has to retest and do all that. That's a lot of waste of effort and doing redundant work to get two products that can be very similar. Why is there not an industrial app store? How come I can't use the same piece of software on many different hardware platforms? Computers can do it, cell phones can do it. So right now we're involved in a project that we're putting together a software flow computer. The concept is to have a cloud that manages the device, and that will be a device management, but then we'll have separate applications, and we will potentially have a cloud-based flow computer as well. So by being able to put all this together, we can now decide, do we want the application to be on a really heavy computer in the cloud, or do we need the application to be down at an RTU level? And what do we need to do to be able to make that portable so you as the end user can choose? So edge processing. This is a very, very, very in-depth at this point in time. Edge processing today equals Zeta Edge, which is the lowest dollars. So the Zeta Edge device that I showed down in the right corner, it is the lowest Class 1 Div 2 edge device that we've seen so far in the market. There are other people such as Moxa and 2 or 3 others that actually have an industrial device, but we've been pretty impressed so far with the Zeta Edge. We haven't seen a ton of applications yet being developed. We've been working with AutoSol Edge extensively, and they've been very good to work with. But we have not seen a plethora like 500 or 1,000 applications popping up that we can drop onto our edge device. So one of the things we have to really think about when we're looking at an edge device is, do we want people to just be able to do custom programming? I mean, we tried that 30, 40 years ago with DOS, where we would have people write their own programs and try to put that into an industrial environment. And you have to be really careful, because now you have to test for a whole lot of things, and it's really expensive. So my advice is get people that are going to develop applications to develop applications, and try not to customize or custom build too many of your own Python scripts or things like that, because I think there's going to be a massive risk that goes with that. So a full stack solution, you can buy hardware, apps, and monitoring service from one vendor. Closed systems that they manage, they collect data and sell you access. Cloud only option, does not cover all operations, usually not domain experts. So that is currently what we get right now. Whereas these edge devices open this up so that we can do a whole bunch of different things. So typically requires, again, other system components. They're not expandable, lack of remote management tools, lack of application, lack of integration of service. So these edge devices fix most of those things and provide a ton of flexibility into the industry. So this is sort of tongue in cheek, but in the oil and gas industry lately, edge device somehow equals spark plug B. Who knew? So we do have a spark plug B solution, which is the SignalFire Ranger. They did a very good presentation a couple of weeks ago on this Automation Village. And basically it's an IO device that has a Cat-M1 cell modem in it, and you just connect it directly up to a broker, and then it talks to wherever you'd like, and you subscribe to the other side of the broker, and you get your data. But we also have things like our safety box. Safety box is a device we have. It supports multiple protocols, alarm callout, historizes data, pushes data. It's been fully tested. It does not speak Spark-Plug-B, but does speak MQTT. And you can configure it right from your cell phone, and it interacts text messages with you on your cell phone, as you can see on the right. So we've been working on this for a number of years. It's been developed. It consolidates a whole bunch of hardware. In my opinion, this is an edge device. But at this point in time, according to my previous definition that an edge device must be Spark-Plug-B, it does not quite pass that, which is quite amazing because we're willing to put out things that nobody's ever tested or worked on because it's Spark-Plug-B, as opposed to putting out things that have been tried, tested on very reliable hardware. Future concept number 4, RTUs will have universal I/O. Delta V has charms. The configurable has, T-Box has configurable DI/DO. There is no reason going forward over the next 2 to 3 years why every piece of hardware that we buy does not have universal I/O on board. I think the prices come down far enough. It eliminates marshalling. And for a lot of these devices, with the price being down so far, we can even get rid of fusing because the risks are pretty low that we're going to actually blow the device up due to a power surge. So it's an interesting market right now. So future concept number 5, custom panels will rarely be required. Device will be modularized, batteries, enclosures. So everything will start to get bundled together in nice little outdoor capable units or indoor capable units, depending what you need. You probably have kits you can just snap around them to make something outdoor rated. We spend a lot of money custom designing panels over and over and over again, and a lot of money wiring out spare I/O and things like that. And we could probably reduce our costs substantially if we can just get things into little environmentally resistant boxes, because all the RTUs and devices, the only thing they're not is water resistant. Everything else they're resistant to. So they're typically class 1 div 2, they're -40, and in the T-Box case, we run it down to -80. We've got some amazing capabilities on these devices, and all they need really is a weatherproof enclosure around them. Future concept number 6. Data will have context. So right now, when we look at data, we go to map data. We have to get it from a device. So it comes in on a 4 to 20 or something like that. And then we have to change it, or a Modbus. And then we have to change it to whatever it's going to be recorded at as a digital. And then we have to put units on it. And then we go and move it over Modbus again or something, some other protocol. And then at the other end, we have to line the units up. And we don't really have any concept of when we get the data. The only thing that's moved is the data, and we haven't moved the units or any of the other things that can go with it. So we envision having data that has a structure to it of some sort. Maybe device location, what process calculations have happened to create the data. In some protocols, they support flags so that when you do a calculation, the data will carry through and say that there might have been a bad value in the calculation, or marked it as an invalid piece of data that's in the calculation, so the calculation will be marked as invalid. Units, the accuracy of what the devices are, and what's it all relative to, and on and on. There's a whole bunch of things that we can start to put into the data that we currently have that's very, very rudimentary. And we do it because we have limited bandwidth. I mean, if we have an infinite bandwidth, we wouldn't be worrying about this stuff. But we do this because the bandwidth is so limited and so expensive. So as we start to move on the previous telecom, driving it, and bandwidth becomes far less expensive, we can move into some of these concepts where we have something very similar to like HART, to what you see remotely. When you go to manage a device, you get all that good, rich data that comes back with your HART data. And those types of things we'll be able to manage around the world and be more effective about. So number 42, if you've ever read Life of the Universe, or actually Hitchhiker's Guide to the Galaxy, and actually I think it's Life, the Universe, and Everything, but number 42 is the answer to Life, the Universe, and Everything. And if you just see the number 42 and you don't have a context for it, it's meaningless. And that's important to understand again. We do need context. So things like my age, the temperature in Fahrenheit, when it was taken, the answer to life, the universe, and everything. So the other thing when we start to look at even bigger concept on data is what's going to happen when we start to have augmented reality solutions. And this is a video Trihedral did a few years ago with the first version of the HoloLens. We're now on version 2. And we actually have a couple of customers that are actually picking up version 2. And part of their research is to actually be able to try out these HoloLenses and make use of them in their workflows and applications. So for me, the whole idea of being able to have your data with you and right on stream with you and riding right in your visor and being able to see things right on the vessel of what actually is going on inside that vessel. And if we could hook that up even easier, and some of the stuff that we can now do in VT SCADA with being able to browse PLCs and those types of things is the next step. OPC, those types of things, to be able to just map tags is the next step to getting fully into our data having context. So number 7, data transforms cost money. So this is something that people don't very often do the analysis on. But when you start at a 4 to 20 milliamp transmitter and you have to turn that into Modbus, and then you have to map that Modbus into a SCADA system, and then you have to map that into your, if your process historian is not part of your SCADA system like VT SCADA, then you have to map that into a PI system, and then you have to map it to SQL Server, SAP. And there's all sorts of things that happen along the way. Either the tag name can change or the data can change. Or even the object can change if it actually has some context to it. And the problem is when we look at SAP, SAP may have, instead of a tag name, what comes from the SCADA system. So number one problem we have is the PLC programmer in the beginning probably didn't have a PLC programming standard to work off of. So he might have called the one tag flow rate, and the other guy might have called the rate of flow. So now we have 2 different tag names for the same piece of data, and it's tough to normalize that. Then when we pass them to the SCADA system, that becomes the cross-wiring for the entire system. So that means that the actual tag that we had that was a 4 to 20 in one system and a 4 to 20 in another system has a different tag in the PLC than what actually happens in the SCADA system. But eventually, we have to get all those tags aligned so they all are called flow rate, so that when we rerun a query on it from an enterprise level system, Power BI or something like that, and we want to check all the flow rates across the system, we don't have to go in and custom map and custom crosswire all that stuff. So as we go through, and one example of this is we have a customer who does 4 to 20 into his RTU. He then does Modbus to a SCADA host. Then from a SCADA host, he goes through BizTalk and changes the tag name to, does a lookup table and changes the tag name to the asset number, which they've just assigned a number of like 33 to, your LSD and your station number and all those types of things, and just to make it nice and simple. But to transform that data is very expensive because somebody has to line all that stuff up and make sure it all, and test it and make sure it all works. Whereas if the tag name just carries throughout the entire system, then you save a substantial amount of money. So we will find the most cost-effective way to consolidate and aggregate data. Currently, we kind of just make it up as we're going along. Future concept number 8, alarm management event will be centralized across the cloud and all systems. This is huge. It's becoming more and more important for people to be accountable with audit trails. The alarm management must come into one place. If it doesn't come into one place, it's very difficult if your PLCs calling out and your RTUs calling out and your SCADA systems calling out and your cloud-based analytics is calling out. It's very hard to synchronize all of those alarm callouts. And especially if you're the person that receives all 4 of those callouts and you want to go on vacation, how do you change the scheduling of those alarms? So I see that SCADA systems like VT SCADA will have a really, really strong role to play in the emerging SCADA, not only because of its data gathering capabilities and things like that, but also I mean, number one, because of the alarm management and the events and the ability when an alarm comes in to be able to actually give an instruction set as to what the operator is supposed to do to optimize his workflow to take care of that alarm and to audit trail that he actually did those types of things. And I mean, we're really moving into an age now where workflows are driving everything. And for an operator, really alarms and events are what drive the workflow. So it's going to be a really, really, really important thing to see how we unify all of that. And with all the stuff we have coming at us now, with sort of all the cloud-based sort of broker type stuff, they're blasting data out to, could be 20, 30, 50, 100 different cloud-based services. So making sure that one of those at least is an alarm and event manager and centralized and somehow is catching the data from all the others is going to be a very interesting exercise, as opposed to, and we'll talk more about architectures later, as opposed to bringing it up into a nice secure place, centralizing it and then dispersing it from there. So we're just going to move into a little bit talking about SCADA systems in general. And right now we have a whole bunch of proprietary SCADA systems on the market. They're siloed. You have to buy their equipment. You can't leave them. They're sort of a hostage situation. And that's all great because it's services, and for them, that's awesome. But for the end user, they kind of get stuck. So number 9, either edge devices or distributed historians will win the day. So interesting enough, where we sit right now, if you look at the concept of having a broker in the middle and then having all of your different products out on the edge just subscribing to that broker, this is where we run into this situation of exactly what I talked about. You need to be able to consolidate all your alarms and all your real-time data into one place for operations, as opposed to some of the other data and things like that that people are doing analytics on. And if you're running alarms back and forth, you still need to probably end up having some interaction between those different products that are out remote and being able to integrate them into the SCADA system so that you can have a centralized alarming platform and reporting platform. So when we look here, the role of the SCADA system. So number one, the real role of the SCADA system, it's getting data reliably on, and typically it's on substandard networks, but it's getting data reliably and it's getting the correct data. And we talked about reliability. Reliability is about not losing data. Sometimes we have to manage and determine what kind of data we have. We have to set different times for when that data is important. Is it have to be updated every second? Did it have to be updated every hour, once a day for a gas well? So those are all the things that the SCADA system does a very good job of sorting how often that data has to be presented. And then we have other tricks to use in the SCADA system, which even if we are getting 1 second data, we don't record every 1 second, we just record the data when it changes. And then when we report, we actually report the data as 1 second because it hasn't changed. So there's some really interesting things that happen with the SCADA system that allows us to get all this sort of stranded, geographically distant data. The centralized alarming piece and alarm management I've already covered. That's a very, very, very important piece, and the centralized audit trail as well from both an accountability and a safety perspective. And then reporting, it's a good piece as part of the SCADA system, but we can also do some pretty interesting things by generating all that data. So instead of the previous slide we had, which shows the broker in the middle of everything, we actually have a system where maybe the broker actually just sits above the SCADA system on the WAN, but the SCADA system feeds the broker, and then we publish all the data out. Because we don't have anything that's dependent on if somebody overloads the broker or does things like that at that area. Whereas down below, if we overload one of our servers or we overload one of our links, communication links, that's a really, really big risk to reliability. So controlling how your data moves and where it moves to, they're certainly very, very important. So data flow. One of the things I think that we're going to see is people are going to become more and more aware of workflow. And as a result of workflow, we have data flow. So when you look at Ian's presentation that he did on Quantum EFM, that is a textbook example of just what they do there saves potentially per well hundreds of man hours per year. There are reporting requirements and things that just bringing into a SCADA system and dumping into Excel and then trying to find the needle in the haystack that is the well that isn't performing or is frozen or those types of things, and doing that manually. People do it all the time, and we have multiple people doing it for the same sites. It makes far more sense to automate those things and to manage that workflow. And you should be looking at all the data that you're gathering and using and bringing it in to your system and figure out which data you actually need and which data you don't. We gather a lot of data in hope that someday we'll be able to use it, that someday Watson's AI will be able to look at all of our data and say, we can make you more money if you just tweak this or tweak that or do this or do that. And that might have a hope, but right now we move a lot of data around at very high frequencies that we don't really need to move around. And we don't tune our systems. I've worked on a lot of SCADA systems where they're polling devices that don't exist. So the devices hit the timeout time every time polling. I mean, they have dead time introduced in the network, and they think they need more bandwidth, and all they need to do is optimize their polling or optimize how they're getting their data, or even move to a report by exception or cryo type scenario for protocols. So this is a quick little video, and I like it from the perspective of it's another HoloLens video, but instead of using data for the real-time operations, they're using the HoloLens to support their actual, get their experts involved and have their experts online. So by having the expert online with them and riding along with them, they can actually maintain and do things much more efficiently and effectively. And the reason I'm actually showing this isn't because I think it's amazingly cool, but I do. But if the technology is going to come for a whole bunch of other reasons, we're going to need to figure out how to leverage these technologies. We're going to need to figure out how to store voice and video as part of what we're doing for our data gathering so that we can roll back and see what happened and see if the person actually closed the right valve or something like that, right? So all of this data gathering that we currently do is a pittance compared to what we're going to do. Video is very bandwidth intensive. We're going to need to figure out ways to analyze it, which we kind of covered in the drone video, to only report on alarms that we'd actually seen in the drone. If you want to go back and see my discussion a couple of weeks ago, you can have a look at that. But this is a very, very interesting, I would say, change in technology, this idea of things like the HoloLens and these displays. So why do we not have a unified industrial solution that includes voice and video? So IP changed the world. Everything went to IP. What IP did is it made it much easier for us to connect a couple of devices, because in essence, they basically had a postal code attached to them every time a message was sent out, that address. We have not done a good job of unifying the technology. And it's amazing right now, because when we look at what's going on in this conference call, we've got Zoom, we've got voice, we've got video, we're recording all of it, and all those types of things. What we don't have are great analytics tools to be able to pick the data out of this entire 40 minutes of what I've been doing, to be able to pick out and extract the key points of data out of this entire multimedia piece that's just been presented. So it's going to be very important that we understand how to deal with this. If you look at VT SCADA's now got a BACnet driver, which is a massive move. They had one before, but they really kind of cleaned it up and sort of taken it serious, which means they're moving into the commercial industries for HVAC systems and those types of things, for plant HVAC systems. And when you look at the convergence that went on with IP, now the convergence is going to go on in terms of data. And we're eventually going to end up in a place, I believe, where we're voice, video, the whole multimedia piece. An operator will just be able to walk up to a site, which he currently can do with Iris. He can snag a picture of a valve as he's doing his report. He can do some voice overlays, and then we bring all that data back into one central location. And I see there will start to become some standards around that, as opposed to everybody, like we've done with RTUs, building their own flow computer and flow calculations. We will start to see some standards move around voice and video. So summary, data is data. It's all IP, voice, video, emailing, texting. All that comes down to are the basic fundamentals of reliability, bandwidth, latency that we require. Augmented reality, It lets us virtualize almost anywhere. We can have any expert ride along with us. Speech to text voice interaction, it's here. We're starting to see it. It's going to permeate. Video alarm conferencing, like we're doing now, is allowing parties to see and hear what we say, real-time assist. Video analytics, they're still developing that, but I'm really interested to see where that technology is going to go, because that's going to make a massive, massive step. Drones and autonomous vehicles are still developing, but they've come so far. We actually see mass commercial deployment of autonomous vehicles. We see videos of Teslas driving from Okotoks to Calgary without any human intervention. Those things are radically going to change what we do. But we're still missing some common standards and best practices. We kind of throw out these things and people kind of glom onto them. And I'm really interested to see where we go here in the next year or two as we start to relax on what's been our main limiting function in SCADA, which is bandwidth and latency challenges and reliability. So that is the end. So these are the references for all the videos. So if you would like to see any of those, please just follow up with this video and you can find them on YouTube.
Absolutely fascinating once again.
Thanks.
Really great job, Mervyn. Yeah, I think that that's when we kind of look at the future. I mean, it was kind of blowing my mind. You know, the start of your presentation in particular, where we had looking at everything from the poor Boston Dynamics robot being nearly assaulted, and was still figuring out how to stand up and try and retrieve that box. And then when you look at the Elon Musk and the whole Starlink program, I mean, it's become so fascinating. I mean, they're looking at 12,000 satellites that they'll have just on that Starlink program. That's what they're hoping to get to. And at one point, and in fairness, you kind of answered it, you know, with when you're talking about low Earth orbit versus a geostationary, the whole thing of latency, and of course by having, you know, low Earth orbit and the vacuum of space, you can have a lot more, I guess, a lot more bandwidth. Because you're not bouncing it along, you know, a longer path, which is a fiber optic cable. Anyway, all that kind of blew my mind a bit. Actually, it was really good. I was geeking out. and just for everyone else, if you have questions, make sure that you type it into the Q&A box as well. So I'm just going to take control for a second, show people where that is, because we've only a few minutes actually left for questions. So that's the Q&A chat box. You just type into that, and Mervyn would be happy to answer any of those questions. You actually covered as well, Mervyn, quite a bit on context, and you said data context. So I mean, have you actually used any kind of more international standards for how to normalize data when you kind of mentioned it? I mean, have you looked at that?
No, what we do is we sort of kludge it together right now. We pull flags separate from the actual data in a sort of pseudo structure that we create at the SCADA system level, but it's actually not coming from the RTU as an object. And I mean, some of the data comes from the RTU as an object or the PLC, but a lot of the stuff we actually do is we set all the flags in the SCADA host, and then when we do calculations, if any of those flags are bad data or missing data or any of those types of things, then the flag carries through with the calculation. But we really don't have any clear standards on that I've seen yet to be able to sort of work with on that side. So we'll see what happens. I'm interested. I mean, I'm still sort of stuck in the DNP3 world and Modbus world and Ethernet IP or SIP protocol world. But I think there's going to be a whole bunch of developments that start to happen here very quickly, especially with the ability to minimize on your transforms and have the structure carry right up from the RTU.
I think so too. You made a very interesting point as well, which was really going back to kind of being, I guess, data efficient and bandwidth efficient, because, you know, you said, okay, going back to 900 and 1200 baud, you had to think very efficiently. And of course, it's one of the things that's, you know, I think it was actually Arthur C. Clarke, you know, the so-called inventor of the modern satellite system, that his comment was always that we'll always fill. It's a bit like we'll just fill our whatever bandwidth we have with whatever like our whole need will change, because we'll actually fill up that bandwidth a bit like that. If you live in a small home, and I often think about this, if you had like a 1-bedroom apartment, you can be very efficient in that space. The moment that you move into a bigger house, you fill it with clutter. And I think that whole side of it is quite fascinating, that the efficiency requirements never really change when you think about it. It's just you need to be efficient.
But what we really have a problem with right now is we don't have a very good classification program, because when we look at a temperature on a vessel that might change every hour or month or year, in a lot of situations we just bulk pull or bulk grab that data the same as we grab the 1-second flow rate that we're trying to grab from it. So we really need to figure out how to move data more effectively. But interesting enough, we're going the opposite way on bandwidth. It's just growing and growing. So I mean, that's kind of proved with computers. Instead of building more efficient code, we built faster computers, and we got more memory. So it allowed people to cost effectively buy their way out of trouble. I mean, years ago, I worked on a project where when we built the project, the DCS designer said, how long until we start up? And I said, 2 years. He goes, oh, good, they'll have a computer built by then that will be able to support the software we have. So it's true. Yes.
So I mean, like if protocols and devices get to the point where they're kind of self-tuning, and you're kind of hinting at aspects of that, like the power of edge computing, etc., so that the device itself says, well, I only need to report at this rate, and it does it dynamically. It figures out its own kind of way of doing it. I mean, you played with a lot of stuff. Have you played with that kind of thing?
So we usually are pretty broad brushed on the self-polling, which is we kind of poll on a best effort basis. Typically, if you get into IP-based networks, they would have quality of service and things like that will actually self-tune the bandwidth, and we would actually prioritize bandwidth years ago. So voice, when we had to have voice on a pipeline, it would always have a prioritized bandwidth over the internet surfing or things like that. So we've done some of that, but at an industrial protocol level, there's been very little of that self-tuning. It's going to be very interesting for an edge device, because the definition of an edge device, I mean, I threw out the SparkPlug-B thing, but it really, VT SCADA has been an edge device for 10 years. I mean, you put VT SCADA on a panel PC, and it is an edge device. I mean, it converts protocols, it gets it all back to centralized historian. It does all the things that an edge device does. So trying to understand that architecture and figure out the best way to manage that, there's a whole bunch of evaluations that people never had to do before. I mean, people before just evaluated a PLC and said, can it run the logic or can't it? And even protocols were relatively secondary, because the PLC programmer usually focuses on the PLC, and he doesn't focus on the enterprise or the business intelligence system, and usually is completely ignorant to it. Whereas now we're starting to look at how do we make sure we get the data into the hands of the CEO for the right reports, or the data into asset management people. And those are the types of things now that we're starting to look at. And if we can come up with a data classification system, I think we'll be able to manage that data more and more effectively. And for me, a mind-boggling change in the industry, and not ours, but like the Uber concept, where they no longer own hardware, they just provide a dispatching service in essence. That changed the whole way that industry and changed efficiencies. And some of those just ideas, when we look at how we manage data and what we do, can actually make a massive impact. So I'm looking to see what those next great thoughts are right now, and we're trying to figure out where we're going to go with it.
Absolutely. Well, we're out of time. So Mervyn, I'd like to personally thank you once again for everything. We got some nice comments in just thanking you instead for an insightful future probing presentation. And so you have viewers in Ireland. Tom, thank you, Tom.
Cool.
so yeah, and from around the world. So thank you once again, Mervyn. And to everyone else, if I just want to save what's coming up. So if you need to change streams, this is what you need to do. Just log out of this this session, and then you can select a different stream. Just look at your invite, and each one has its own invite. And if you then want to know what's coming up next, well, we have Mark Reski and Tyler Davis in the oil and gas stream. So we're looking forward to having them very shortly. We've about 6 minutes if you want to go and take a break. So go and take that restroom break or whatever else you need to do. Make a quick phone call, and we'll see you back here at the top of the hour with Mark and Tyler. So thank you. And welcome back, everyone. So very shortly, we'll be starting our presentation with quantum engineering, and we will have Mark Reski and Tyler Davis. So let me just bring the guys up here for a second, and hopefully you've been enjoying this show as well. Lots of information. So okay, so I'm just gonna get the guys in here. So Mark. There you are, Mark. And hey, Tyler, how are you guys?
Good, how are you?
Doing great, thanks. Yeah,
well, very well.
Thank you both very much for joining us. It's great to have you. And yeah, so Mark, you're the VP of Engineering.
Yes.
Yep. And not sure if you want to give a small bit of your background as well. Just
my background has pretty much been industrial controls, pretty much since I was born. Been in my family for a long time. My background's electrical engineering, and I've just enjoyed it. It's kind of one of those things when you see it on the Science Channel, you see how things work. I've just been fascinated. So
fantastic. No, absolutely. And Tyler, so you're a network and process technician as well. So yeah, what's your background? You said you're about 20 years, I think, in the
yeah.
Is that just with quantum?
Not with quantum, just in mechanical, electrical diagnosis and control systems. Working for an educational system here in Phoenix, Arizona for the last 10 years. Prior to that, doing plumbing, automotive, heavy industrial motor rebuilds.
Neat.
A little bit of everything, and just gaining experience as I go every time. And more recently, got heavily into the networking side of things. And
here you are.
It's just eternal learning and improvement.
Absolutely. So yeah, you're going to be covering its network connectivity concerns for geographically challenged systems. So yeah, really looking forward to hearing about that. As always, if anyone has any questions, make sure that you type it in. Just click into the Q&A button at any time. You can, and preferably if you can do it earlier rather than at last minute. And I'll be happy to pass on those questions on to Mark and Tyler. So guys, I'm going to give you control, and if you have your presentation ready to rock and roll, and off we go.
Let me set her up here, and we'll get going.
Sounds good.
So. Right.
And we got you. Perfect.
Okay, we looking good?
Looking great. Perfect. Thank you.
Okay, wonderful. Yeah, so if you joined me a few weeks ago, I did a quick presentation, a lot of the similar slides, but I wanted to dive into it a little bit more in depth of what a geographically system is, or challenge system is, and things you can do to help improve your challenges that you're experiencing. So as Peter introduced us earlier, I'm Mark again. Tyler is along with me. He's our CCNA certified engineer on staff here that helps out with our network designs and security improvements for a lot of geographically challenged systems. So what's a geographically challenged system? It's not at a plant. It's not at the oil refinery. It's not at the water facility. It's not at the food and beverage plant. It's remote. And as you can see from these photos, I got a remote wastewater lift station. As you can see, it's just a generator and a panel. We do some mining applications out here in Arizona too. They got to monitor various levels, tanks, chemicals throughout their whole territory. And then we have a lot of natural gas out here that we help out with clients. A lot of municipalities have that. As you can see, that's just a big monopole with a solar cell, and what they got in there is, pressure gauge and a small PLC in there. And then another thing is the water booster stations that are spread out all over the place, and that's similar to, midstream pipelines and well sites to deliver oil and gas. So the one key thing that you can kind of notice in all of these photos is there's actually an antenna mounted at every one of these sites. It's kind of hard to see in the wastewater one, it's a little chopped off, but that's kind of how you can determine if it's a remote site. Now, there might be an application where it's a satellite, link. We've had those before. It could also be cellular. So basically what it comes down to, it's some sort of wireless connection. You don't have the option of Ethernet or fiber. So we'll go to the next slide here. So it's really important that we do proper planning for geographically challenged systems, well sites, and that kind of stuff. If you don't do that, there's a lot of unfortunate consequences, is the best way of putting it. You can get poor latency, response times back from sites. You could have operators just constantly clicking that mouse, click, 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 click to send a command. And that in itself is dangerous. That's poor design, that's poor coding, it's just poor all the way around. The other thing I've seen is I'll show up to SCADA applications where they've got the alarm banner on one display, and then they got their graphics on another display, and it's just constantly scrolling with comm alarms, communication alarms, lost to site 5, lost to site 3AB, and it's just constantly boom, boom, boom. And when your alarm banner is getting full of those and populated, eventually alarm fatigue kicks in, and then operators miss real alarms, and that is detrimental in itself. There's a lot of consequences with that. So we got to try to minimize that stuff, and that's what we at Quantum try to do. We try to eliminate a lot of that stuff. We try to provide a little extra improvement and tweaking to fine-tune the systems. That kind of segues into what I was saying earlier about impacts to the production or process. The other big thing is you bought a control system to automate things, to have less personnel running it, and less manning of equipment. But if you're having people throw stuff in manual because you have poor communications, what's your return on investment? Good. In my opinion, no. If you got to staff more people because your control system isn't working effectively, yeah, your ROI is not good. And there's some places where they've just been in complete manual control. I've seen. We've helped improve people or help improve systems that have been in manual for years and years and years, and we've wound up getting them reconnected by different means of cellular or wireless, and then making tweaks to the network. Another good improvement is you really need to understand the limitations of your control system and the software connecting to your control systems. So one of the things that I preach heavily, and it's been very difficult to get it across to people, is network segmentation. And unfortunately, a lot of designs are done by large civil firms and environmental firms, and they're not as proficient as someone that specializes in the industry. They don't have a network guy. They might have a network person at the corporate level, and they're more worried about maintaining emails, Word docs, and that kind of stuff. But it's different. We got to maintain, flows. We got to maintain valves. We got to make sure things turn on and off properly. Otherwise, we could lose control, and there could be environmental impact. Someone could get hurt. It's a safety concern. So our world is totally different than the corporate IT world. We've all heard the word OT, operational technology. So we got to keep that in mind. Network segmentation, that's huge, and there's a lot of benefits on that, from security to broadcast traffic issues. The other big thing is you got to know the protocols you're using: Modbus, Ethernet IP, DNP3, Profinet, Profibus. We got to know what's going on back there on the back end, and know the limitations of that. You want to reduce the packet size, the amount of data going across. And one thing in the Allen Bradley world is, we like to use tags, and you can go up to, I think, 32 characters right now. And GE just announced that they're going to be supporting 128 characters, which is kind of insane. But each character requires a bit, and that's got to be transmitted. So the more bits you have, the more transmission you got to use. Leverage communication protocol drivers that allow you to do better timing and sizing control. So what I'm showing here in the pictorial is VT SCADA, who's always had a very good ability to set up polling. Other manufacturers out there like Kepware have the option, but to be honest, to the best of my knowledge, VT SCADA has been kind of in the lead, in the forefront on that. And it's actually worked out really well for applications we've done where we need to slow the polling down for certain areas, just because we're doing 100 megahertz wireless systems versus 900 versus cellular. So take a look at the polling driver if you guys aren't leveraging that. If you're a VT SCADA user, it's great. If you're not a VT SCADA user, don't worry. There's other people out there that can help you that specialize in driver writing. The other big thing is, the spoke and hub architecture. I'm not sure if you guys are familiar with that, but it's just like a wheel. At the spoke or at the hub, we got, a master PLC, and it's going out and it's pulling each of the individual sites, the spokes, one at a time. So it's kind of managing it. That model has been around for decades, and it's been very effective, but it does have some limitations. So we got to balance out the systems, of pros and cons, or strengths and weaknesses. And that's the data concentrator method. And then if you implement messaging controls inside the PLC and stagger stuff a little bit better, you're going to see some improvements there. I got some feedback on this slide, and it was good. Someone liked my analogy that will pop up here soon. But what I'm showing here is we got two PLCs on the left and the right. They're shown in white. And then I got two 900 megahertz radios, and they got to communicate to each other back and forth. Very simple architecture. It's done all over the place. It's nothing new. What's unique about the architecture, as you can see, there's 100 megabits, not bytes, bits. It's very important to know the difference. Bits are smaller than bytes. And then the radios communicate with each other via 1 megabits per second, significantly smaller than the 100 megabits per second. So, this next little pop-up here is what I consider the equivalency. It's taking a fire hose, trying to connect it to a garden hose, and then connect it to another fire hose, and try to get all the same flow rate and pressure that a fire hose would get in the middle of the garden hose. And I'm pretty confident the garden hose is going to burst and blow, and that's going to be your failure point, or the weak point, where things start to fail. And oddly enough, that's where we see a lot of problems occur. Is you got a big pipe going to a little pipe, and then you got a big pipe. And just because you have an RJ45 port doesn't mean you're going to get the same speeds across everything. So you got to really understand that you got a bottleneck somewhere. You got to understand your technology. You got to understand what you're using. So you can work around that. 100 megabits connected to 1 megabits, connected to 100 megabits. That's doable. There's nothing wrong with it. You just got to understand the limitations and work with that. And unfortunately, a lot of people don't take that into consideration. So that's okay. The other thing you want to look at for wireless systems is a lot of people just look at the received signal strength indication, the RSSI. And it might say, minus 60 dBm, but your signal to noise ratio will be horrific. That means that there's just a lot more noise. So you got your signal here, if you're looking at me, and you got your noise floor. Normally it's down here, but if we start to raise that noise floor up a little bit, the likelihood of actually getting the signal through is difficult. So it's kind of like, a party. When you're first there, you're able to talk to a couple people easily, but as soon as we start introducing 10, 20, 30 people there, we're yelling, we're screaming at each other. And you can get every word, you might be able to figure out what's going on, but then there's a point where it just becomes difficult. So the signal to noise ratio is very important. So always look at that also in conjunction with your received signal strength indication. So what I'm showing here is a slide, and I didn't get to go into too much detail with it last time. I'm going to dive into it a little bit more, and then Tyler will probably expand on some concepts here in a little bit. But what's shown in orange is a typical flat network where all the IP addresses are the same. The subnets are the same. Everything can communicate. And what we're showing here with the circles are broadcast traffic. So the circles are going everywhere, the orange circles. As you can see, they're going to the VT SCADA computer. They're going to all the PLCs. They're going to all the OITs. And what we're trying to extract are the little triangles from the PLC up top, the VT SCADA. And so as you can see, we got the orange circles and the triangles going through the wireless system just fine. But that's we got some extra traffic going across with the orange circles. It doesn't need to be broadcasted across. So how you can accomplish preventing that broadcast traffic from propagating through is start to leverage layer 3 networking equipment and layer 2. So layer 3 is basically where you start to get the router level in there. I'm just quickly summarizing it. I'm sure Tyler could provide more detail on that if he dives into it. But what happens is it prevents the broadcast traffic from going across. So if you look on the far right side, we got 4 different areas in color. We got a green, a blue, a red, and a yellow. And as you can see, the green circles, the blue circles, and red circles don't traverse the wireless network there. So what we're doing by creating different subnets and isolating the networks is we're not allowing broadcast traffic that's not necessary to traverse the slow network communications. Like I said earlier, we might have a wireless system that only supports 1 megabits per second. And if we're using up that precious bandwidth for something that's not needed, then we're just impacting our system and our reliability. The other thing you want to keep an eye out for is unicast and multicast traffic. That will also be a big problem there. To dive into some improvements you can do on the PLC end, this is an example for an Allen Bradley PLC, fairly common in a lot of the projects we work with in oil and gas, water, wastewater, mostly in the United States. What I'm showing here is 2 UDTs. They have the exact same information inside them. They have start commands, speed commands, faults, feedback, auto. You can see them all. The only difference between the 2 screen captures are the fact that I structured the UDTs, the user-defined data types, differently. So as you can see, I combined all the bools into a chunk, and I combined all the integers into a chunk, and all the reals into a chunk on the start 2 UDT. If you look at the start 1, it's got a bool, real, bool, bool, and it's just kind of not organized. So how Allen Bradley compiles these things is they actually have to use a chunk of bools to make up just that one bool in that area. So if you compact all the bools together, you're actually combining the data better. So as you can see in the red boxes there, the STR1, start UDT1, has 28 bytes of data. And if you look at the start 2, it has 16 bytes of data. So as you can see, by just structuring your UDTs properly, we've already reduced data throughput by 12 bytes, which can be precious. So, and if your UDT is really big, think about it. You might get a lot of benefits there. That means a lot less data has to be transmitted across. So keep that in mind. Keep your tag names short and compact stuff. Only bring across what you need and understand how your systems work. So with that in mind, I'm going to pass it along to Tyler here, who's going to provide a little bit more detail on various protocols that can assist you. And the one thing to keep in mind is we're considering the fact that you have managed equipment, not unmanaged switches. So just keep that in mind. Tyler, are you there?
Yep, I'm here.
Awesome. I'll let you go ahead, and I'll drive for you. So just let me know when you get the next slide.
As Mark said, the protocols and ways we're going to streamline our networks, or we attempt to and do, is reliant on managed routers and switches. The network segmentation could also be known as VLANs or virtual LANs, where we create smaller broadcast domains to limit that traffic so that every PLC doesn't need to see the broadcast from every other device on the network. And sorry, one moment. And a unmanaged switch isn't able to handle separate VLANs. So unmanaged equipment really won't work for reducing the size of your networks that are existing. And a managed switch or layer 3 switch and router can provide a lot more fine-tuning capability. And yeah, so before I get into this first slide, spanning tree protocol, I created these slides based off of jobs I've done here with Quantum and in the past. I wanted to I think the insert slide I thought about is time. NTP, a time server on your network is necessary to reduce the amount of security handshakes, to keep everything synchronized and reduce drops because protocols timeout, where a packet from one unit has a date from 2 years ago, a router will drop it because it's old, it's expired already by the time it reaches the next hop. In that, once you get everything synchronized on your network, time-wise, then we can get into fine-tuning some other options in the router. Number one I like to look at is spanning tree protocol. Spanning tree is built inside layer 3 switches, routers, to prevent, number one, it's there to ensure that if there is a redundant path, it can be switched to quickly. This provides reliability, high availability, and
so explain the network architecture we're seeing here.
Yeah. So between, if our SCADA server is at switch 1 and a packet being sent across the network will go from switch 1 and first be broadcast to switch 2 and 3. The link in yellow between switch 2 and 3 would be normally a redundant link, and it could potentially create a loop in the network. The packet would continue to loop back from 1 to 2 to 3, and then from 3 it would go to 5 and maybe back to 1 because switch 3 sees that packet coming directly from switch 2. What spanning tree will do is see that packet coming from a secondary path, and spanning tree can turn off the interface. It doesn't power it down, but it can ignore that interface so that the packet will only come in on the original interface from there forward.
So the spanning tree in this example, as I can see, Tyler, would be between 2 and 3, where we would probably make the break. Is that correct?
That would be, yes. The yellow line at switch 2 would be turned off, and that would provide, SCADA would still have access to switch 2 and switch 3 and switch 5. But if the access point wireless at switch 2 is our main access point for a remote network at switch 4, cross wireless, when spanning tree begins to work and it turns off that redundant interface, we've also turned off our remote connectivity to switch number 4 and site 4. And because it's a wireless link between 2 and 3, it will not fall back to that link unless we fine tune the spanning tree protocol. Spanning tree calculates cost based on speed and efficiency, and having a fiber or copper link between switch 1 and 2 will throw a calculation into the main link determined as the copper line, and it will ignore the wireless link. If it's satellite, Wi-Fi, cellular, whatever it is, it will never be as efficient as a hard line between 2 sites. Within spanning tree protocol, this would be, it could be a checkbox on your existing router, I like Cisco equipment. That's where I got most of my training. If you have somebody that knows the command line interface, you can gain very granular control of which ports are designated as root ports, and which ones are the designated alternate ports. If they are copper or wireless, you can still program that directly in to the protocol. And yes.
Sorry, you know, I just had a kind of a question while you're on this.
Yes.
So you know, you say like that the cost of a path it's determined by speed. So it's purely network based for the most part. But can you put in other parameters that would actually say, well, okay,
you can
define one and then maybe actual real cost, you know, because satellite could be more expensive from a data point of view. So maybe you change over to.
Absolutely. Yeah. I was thinking that too when I said cost of a path, because you know, licensed, unlicensed radio, satellite, and cellular have absolutely different monetary costs. The cost I'm referring to is assigned within the protocol as far as the medium is concerned. And when we configure our routers and switches, we can determine whether we want to use that wireless medium or the copper medium and artificially change the cost within the router to the medium we prefer.
Makes a lot of sense.
Does that make sense?
It does.
And
Absolutely. Yeah, thank you.
I think one other thing to bring up, Tyler, too, and from past projects we've experienced, is that there's different versions of the spanning tree protocol also, right? Where that, you know, if you don't have the right versions going on in different switches, just because you turn spanning tree protocol on, you know, to prevent loops, which is what you were talking about, you could actually prevent or cause bigger problems, I think. I've experienced that in the past, and I'm sure you could probably enlighten people on that.
Yeah, there's definitely, when a packet is broadcast or moving through the network, trying to think here.
But I just think the key thing to take away is that, you know, that there's different versions, you know, of the spanning protocol that you got to keep in mind about and watch out.
There is a rapid, updated over time. It will be our rapid spanning tree protocol, which will enable you can define your primaries and your default ports, so that in the event of a packet coming in on 2 ports, you have predefined which port should be shut down in that event, and that packet will no longer loop through the network and create a broadcast storm, or just continue to overwhelm the network where you are paying for your satellite, your cellular, or licensed radio.
Do you want to move along here on the next slide?
Yeah, we can go to the next slide, because it along with the spanning tree, once we've sorted out our costs and which ports we want to use, an access control list is something we can use to limit the types of traffic that are moving across the network. An access control list it's going to be in the web interface of your router, if that's what you have. It's in switches and routers. It is a basic rule set, the most basic form of kind of security, where security starts on a router or switch, and it's also used to fine tune what devices have access to the rest of the network, or a segment of the network. The rules, there's only 2 actions a rule will do, is either permit that packet to travel in the network, or deny that packet from going any further on the network. These rules can be determined based on a protocol or an IP address, or it can drop an entire network except for a packet for a certain destination IP address. A quick example I put in was, a Modbus device probably doesn't need to be getting an HTTP request unless, it will depend on the PLC or the device on the other end, and we will determine what protocols should be allowed to get past the switch.
So that's residing at the layer 2 level with the switch, like at switch 1 and switch 2 then, right?
Yes. And it can be placed on any interface. They can be placed in either direction, going into the switch or out of the switch, one per interface. A word of caution about access control lists before you implement them is that there is an implicit deny rule. So if you just turned one on, you would instantly deny traffic on that interface in the direction that you chose. One moment. So you want to craft your access control lists to deny the type of traffic that you have determined needs to be denied, and then allow the rest of the traffic that is necessary to the network.
So there's two kind of benefits that I'm kind of gathering here, Tyler, from this, is that we can minimize the traffic over the network. So if we have a small pipe, we can kind of consolidate that down to just being Modbus or Ethernet IP or whatever we have. But it also kind of introduces a level of security in there too with the access control list, because if we're saying drop HTTP traffic, that means that traffic's not getting through. I mean, that's kind of what I'm gathering from the statement, right?
And it is kind of the most basic form of security. So it's going to read each packet and filter it based on what you defined. There are ways people can go around and spoof, so it's not a substitute for a firewall, but it is the most basic rule set you can use to protect your devices.
I mean, you're doing something that's better than nothing.
Yeah,
so.
something is better than nothing there.
But even from like purely, just the whole protocol management, because obviously some protocols are kind of, more chattery, maybe, to use a term, than most. So along with it being, well, it's kind of going back to your point earlier, Mark, when we're, you were talking about network segmentation, but purely from the efficiency point of view, to have lots of different ways of being able to segment the network from an efficiency point of view. It might even be from, to a certain extent, a risk point of view, because obviously on low grade, low security or non-encrypted links, if you can actually parse those and keep them to one side, it helps. It helps the next layer of security at least. Yeah,
that's another good point.
Yep.
Yeah, like I said earlier, there's a lot of benefits by just implementing one thing in place. You get a lot of other benefits. And people are surprised when they just do network segmentation, how much of an improvement they get across on a lot of stuff. And then when you start to add on some of these other features that come with layer 2 and layer 3 devices that you don't get with unmanaged switches and devices, it can make a big difference on how your system operates.
Yeah, so. Very good.
Did you want to move along on this one?
All right. The example in the working coming from a real job that did here was traffic coming from our alarm dialer. So the red phone in the diagram there was being broadcast. It was calling home, but hitting switch number 1, it was allowed to broadcast across the wireless link and to the OIT and PLC down there, which it should have nothing to do with it. It really doesn't, shouldn't be allowed there because of the cost of a cellular interface or satellite, and just the cost of the amount of traffic we are putting across our 1 megabit connection if it's a 900 megahertz radio. So applying an access control to the outgoing radio on switch 1 will just stop that alarm dialer from reaching the rest of the network. That is what I was portraying there, and switch 1 will forward that traffic to the router, which then would know how the dialer wanted to get out, what address it wanted to call home to, you know, act as a watchdog, make sure it was online, or maybe it was an actual call going out. That's what I was trying to show there.
Okay. Cool. So basically, you were preventing the traffic from the phone from going down to switch 2 and hitting that OIT and PLC, which
exactly
doesn't need to go there.
Unnecessary traffic for that segment of the network.
Yeah.
And
move along to the next one.
There, yeah, we can move on to the next one.
Cool. So I guess now it's just a summary. I mean, we wanted just to talk about the fact that there's a lot of things you can do in a lot of ways to improve your system. You know, as Tyler said, you know, the cost of data in multiple ways, just performance, and also we're talking about the real dollars, right? And they're tangible, and someone's got to account for that, and someone's got to pay for it. It's precious in a lot of ways. So to summarize, network segmentation is huge. There's a lot of benefits you guys will get from that, just in general. And you can ask any IT guy about that, and you'll learn that there's a lot of improvements. Again, learn about your hardware, optimize any kind of special code, UDTs, tag size, packets, pack your data. Understand your network limitations, understand how your radios can work, understand you're going to have degradation during storms. Can you handle that? Also, we highly recommend using managed switches over unmanaged switches. There's a lot of reasons in there. Even if you don't implement it right away and you just let it sit there dormant, be managed ready is the kind of word I want to say. Because later on, even if you have a small system and you don't need it, you're probably going to need it later. Just do it, do yourself a favor. It'll help you out at the end of the day. And try not to mix match that with managed and unmanaged switch. As Tyler said, create some access control lists to prevent, you know, like the voice over IP communications from traversing into PLCs. That application, I think, was in Douglas, Arizona, and they needed an alarm dialer. And it was a flat network because it was designed by a civil firm, and we were having some issues with the wireless working between some sites, and he made some improvements and some tweaks there, and we saw a great improvement there. Spanning tree protocol, prevent loops. Loops will destroy you. I've been to many sites where there's been a cable in the bottom of a panel, and they just take it and they plug it back into the switch, and oddly enough, it was already in the switch and went back into the same switch, and then all of a sudden the whole facility went down, remote sites were out, and it was pure chaos. So spanning tree protocol will help prevent that, but it's also, you know, key to understand all of it.
Understanding it and defining the roles that you want each port to have.
And there's different versions of the spanning tree protocol. I learned that one time in the office setting up a demo that they have to match. So and that's why I'm not the expert in the networking area as much as Tyler, but I know enough to design things properly. So those are some key things that you can take away to improve your system. We've seen a lot of customers be happy with network segmentation. That's really where they've seen the improvement. So that kind of leads us to the last slide, you know, of questions. Hopefully there's some people out there got some questions. If they're long, detailed questions, you know, you can always reach out to us through our website and we can talk to you in person. But if we got some short ones, I'm willing to take them, Peter.
Yep. Well, I think actually as you were going along, I could see people starting to type and you answered their questions. Well, that's the thing. And maybe even my interjection there answered more. So just to remind everyone, if you do have more questions, please type in that Q&A box as well. So that's your, let me just bring it up again, just in case you're trying to find it. So it's the Q&A button. Sometimes people were typing into the chat part and it was going elsewhere. But
yeah.
yeah, so I mean, like certainly from a network segmentation point of view, you know, that becomes critical. You've gone through that. What are the, you know, the more challenging protocols that you've had to deal with to try and keep segmented? You know, or have you any examples of any kind of projects? You don't have to name names,
Yeah.
but you know, where you started off, because I mean, you know, you said it, Mark, that you need to kind of start with the kind of like with the end goal in mind. So don't start with an unmanaged switch and then expect it all to work beautifully. You know, start from a managed switch type perspective, and then try and you know, use that to scale up your system as your needs change and evolve.
So yeah, to kind of answer that question, there's two parts to that. You can see it from a corporate IT level to a controls level, and you know, we're going to focus more on the controls level here. But what I know as being just hogs on the network, unfortunately, is one of my favorite controllers, Alan Bradley. The Ethernet IP is just, oh God, I don't even know how to explain it. It's just very challenging over wireless. There's a lot of headaches in explaining it to people. But then if you look at the corporate side, you know, voice on the quality service is the highest priority on a network. So there's some stuff that you can change. We don't want voice to be the important thing on a control network. So a lot of those switches, we want to flip the philosophy so that we can improve things better. Voice really shouldn't be on your control system, but hey, some people have it because they need a phone out in the remote area for safety concerns. Who knows? You know, we could come up with tons of ideas. But yeah, I would say Ethernet IP has probably been one of the ones that I've seen that is just the most painful on wireless systems and geographically challenged systems. You know, I've seen people do Alan Bradley and then convert everything to Modbus, because Modbus is a little bit more forgiving over wireless. It's a little bit more deterministic than characteristic for data size. So I have customers that have Alan Bradley right on wireless systems, and they're doing Ethernet IP communication. And then I can go to a similar installation where they decided, hey, we're going to do Modbus over the radios instead, and they still have Alan Bradley PLCs. And that customer actually has a flat network where they're using Modbus, and they have a lot less problems. I've been encouraging them to go away from the flat network, but it's just interesting to compare two almost identical systems, as where one uses Ethernet IP and the other one uses Modbus, and it's just totally different. And they use the same radio hardware.
Sure. So I mean, like, you know, with the advent of you know, digital radio systems, I mean, you know, once upon a time, I did I used to, you know, huge amount of work on radio systems, and trying to traverse SCADA, and even at the start of the cellular world. And one of the challenges was, you know, just literally trying to get those kind of protocols, similar ones that you mentioned, just to remain stable, because they couldn't deal with the network fluctuations. So, yeah. I mean, when you're trying to build in the resilience into that network, and great, you've maybe you fixed loop problems. That's great. So you could actually have a stream of data that is going over a wireless hop, and a thunderstorm arrives, and your expensive one might be, I don't know, maybe it's you know, through someone else's network. I don't know. You pay per use nearly on it, and if that second network, you know, in terms of like, if the first one is essentially, if the protocol is kind of stuttering almost, it's breaking down on that link, and you fail over to your other link, you know, so does STP help? In terms of, you know, make sure that the right packets are going to reach their destination, or is that really a protocol issue, a hard protocol issue, if you know what I mean?
I'll add something, and then Tyler could probably add a little bit about STP. But you know, a lot of the radio manufacturers these days now are small layer 3 devices, so they can route. So for example, we're putting in some GE MDS radios, very common in oil and gas. The new orbits are actually layer 3 devices. They have routing capability, like I mentioned, but they can actually be ordered with cellular and 900 megahertz. And they will actually determine, based on how you're set up, if one link goes down or is having a problem, it will automatically flip over. So there's kind of some improvements just in the technology and where edge devices are being installed. But you know, in regards to the spanning tree protocol, I think Tyler could provide a little bit more input on that, if that would, you know, help out determining the path, Tyler.
Yeah, absolutely. Spanning tree is capable of noting, it stores, you know, which ports it blocked voluntarily. And then if, like you said, a thunderstorm rolls through and our wireless signal is unable to pass, send or receive at that point, spanning tree will know that no packets are traversing that section of the network and automatically switch back over to our hopefully designated alternative port, providing the reliability, high availability that we need. And until a certain point, you can also define how long it will sit on the alternative port before it attempts to move back to the root port.
So it doesn't go stale, because obviously,
yes.
yeah, and protocols. I guess, you know, one of the key things is, you know, when protocols that are more resilient, they're time stamped. It's not really as big an issue, you know, from source to destination to handle it. But really, you know, when you talk about Modbus and some of those protocols you mentioned, that aren't, you know, don't necessarily have any time stamping, that's really where it comes in, you know, and it essentially becomes conflicts. So so that's been very, very interesting. Yeah, absolutely. By the way, we've got lots of comments just saying that we've no questions, but great presentation. So thank you both for that very much. You know, so yeah, you've covered some great topics as well. And so any like in terms of where people can find more information, you know, or like with Quantum as well. I mean, where's the best place to go? Or
you can find us on LinkedIn. You know, Quantum Engineering / Quantum Integrated Solutions. We have an engineering group and an integration group. Our URL is quantumengr.com. So you can find us there. You know, and if you guys need help, you know, more local, you know, I'm always a little hesitant on talking to salespeople because they want to sell a device, but, you know, reach out to an expert that's kind of agnostic. That's really key, because I've seen people have been sold on technology that will help them out, but, you know, always ask someone that's agnostic and doesn't sell an exact product, because you're going to get a better opinion. So, and that's kind of where we try to guide our customers and clients.
And we share that same guiding light, because we're agnostic to hardware.
Exactly. Yeah, and which is great. You guys work well with a lot of stuff.
To do that. Yeah, absolutely. So look, I've no more questions have come in, but I just want to thank you both very much for your time today. And that was really good. And I know from the Thomas people got a lot out of it. I certainly did. And hopefully we'll see both of you along with our viewers as well watching in on this. We'll catch you on the next virtual trade show, which is well, we're saying we're going on. Excuse me, we are going on the road, so so virtually. So it's very careful. We're live in Chicago next week, not live in. You get it? Anyway, and everywhere else. But so we'll bring some more fun into that next week as well. But if anyone you know, has an interest, or if you think someone else is interested, you know, has some interest in attending this, please share the links. It'll be on our websites, etc. There's information and links as well on your registration for Quantum and for our other presenters. And you know, so look, check by, and you can find all that info as well. And so once again, Mark and Tyler, thank you so much for
wonderful. Thank you.
That, and thank you to our viewers. And we see you at the next trade show. Thank you.
Wonderful. Thank you.
All right. Thank you, Peter.
Bye, guys. Bye-bye.
Bye.
And I should say that recordings will be made of all these presentations, and we'll share those over the coming weeks as well. You see them on our YouTube channel, and there'll be links and information as well throughout our website in our Automation Village part. So once again, thank you so much. Have a great day.